Hi guys, am I audible, visible? Hello everyone. Am I audible, visible? Hi guys, am I audible, visible? Hi students, can you see me, hear me? Hello, good evening, welcome to Unacademy NEET English. I'm your biology educator Ambika Sharma. So welcome to another marathon session, and today let's finish molecular basis of inheritance. So after completing this chapter today, we are done with the genetics and evolution as well. So bache, the major portion of your class 12th syllabus will be completed. So how are you? Good evening everyone. Good evening, very good evening. So quickly share the session link with others as well and let them know that ma'am has started the class, and let's talk about this chapter. Okay, and why such big words are there in the chat section? Trust. Oh ho ho, what happened, Hasar? Good evening people, good evening. So quickly share the session link with others as well, and let's start the molecular basis of inheritance. And honestly tell me, how many of you hate this chapter? Yeah, good evening. Wow, Muhammad Nabil, thank you. How many of you hate this chapter? Literally hate this chapter. Good evening everyone, good evening. Yes? First half, second half. I love this chapter. Me too. I love this chapter. High weighted chapter, ma'am. Exactly. It is a high weighted chapter, and from this chapter 6 to 7 questions are expected. Imagine 6 to 7 questions are expected. Means 24 plus marks. Okay. Okay, and not just 6 to 7 questions, 8 to 10 questions can also be there. So yes, it is one of the most important chapters. This is what we are going to complete today, and you should finish it first, because then you will have sufficient time for the revision. And that's my suggestion, students, that please do not go for such topics like the newly added topics first, because see, they are new. You are not used to that topics, right? So it will take a lot of time for their revision. As of now, you should focus on scoring more marks. Okay, so you should complete that chapters, that topics first that you have already studied once. Okay, right? So let's start the session. Let's start the molecular basis of inheritance, and here is one update for you. So this video is very important for all the NEET aspirants, right? Today itself I posted this video, and bache, here I told you about the forms other than NEET that you people should fill. Okay, and do check this video, because in the month of January and February, many entrance forms, they will be out. No doubt we focus majorly on the NEET, right? And we literally want to qualify the NEET examination, but sometimes, you know, because of some variables, some other factors, right, might be you don't get such good marks. So in that case, you should have plan B, right? And these entrance forms, they are very good. These courses are also very good, so you should give it a try. Okay, you should give it a try. Done, bache? So do check this video. Okay, and if you want to join our NEET Endgame, you should join that batch, because in that batch there will be a proper revision, students, right? Proper revision of your class 11th and 12th syllabus, and that revision too with your, right, with your PYQ practice, with your doubt sessions, right? So in next 100 days we are going to start the batch from 2nd of January, and in next 100 days we are going to complete your syllabus. Imagine. Okay, so that this batch is literally going to be a fast track batch, and it's not like that we are directly going to start from the most important topics. No, not at all. We are going to start from the basics, and then we will, right, then we will move towards the advanced level. So you people should definitely join this batch, right? So here in the video you can see the link is there. So Ambika 10 is the coupon code that you have to apply, and you will be the part of this batch, right, bache? And now for early birds, this batch is at a price of 7,999. Okay, with proper revision you will cover all your syllabus. So see you all in this batch, and let's go. Let's start the class, that is molecular basis of inheritance. So first of all, let's see this new syllabus. Okay, so many of you you people are aware of it, isn't it? Right. So here in this chapter we talk about the genetic material. The DNA is the genetic material. In detail, we have to discuss the structure of DNA as well as RNA. That's what we have to cover. We need to talk about the DNA packaging. We need to talk about the replication, central dogma, transcription, genetic code, translation, gene expression and regulation, right? Genome and the Human Genome Project. Finally, DNA fingerprinting and protein biosynthesis. So many students, they ask me this, right? Many students, they ask me this, right? That ma'am, what about this new topic, right? Protein biosynthesis, isn't it? It is also added. Do you know what we need to study here in protein biosynthesis? Yes, Saucy, everyone here in the class? Mr. Blasted, the fees initially it was 4,999, right? At that time you, yeah, the fees was less, but now this batch is at a price of 7,999 only. We'll try to do something, but as of now we have limited seats and you really should join it. Proper classes will be there, chemistry guri, proper classes will be there. Okay, so do you know about this topic? Tell me quickly, do you know about this topic? Protein biosynthesis, yes? Yes, bache, even there will be a proper mock test. Tell me quickly, students, we need to finish this chapter. It's a lengthy chapter, so the session will go for 8 or 9 hours. So let's reduce the duration. If you people will be focused, right, bache, then we can complete this chapter in 7 to 8 hours also. Okay, so let's start it. So here you can see the new syllabus, and you know that one topic is added here, that is protein biosynthesis. In general, what is protein biosynthesis? I'm going to start from this part only. It actually consists of 2 processes. Ultimately, you can understand it, it's protein biosynthesis, means formation of the protein. And you know that how protein is going to, right, how protein is going to form. We know about the central dogma of information, that there will be DNA, then that DNA will form mRNA, that mRNA will form protein. So bache, when DNA, it forms the mRNA, we used to call it as transcription, isn't it? We used to call it as transcription. And when it comes to the formation of protein from our mRNA, we call it as translation. So basically, for the biosynthesis of protein, for the formation of protein, there are 2 processes, that is transcription and translation only. So here there is nothing new that we need to learn. We just need to revise the transcription as well as the translation for the protein biosynthesis. So there should not, so you should not confuse here. Okay, done bache. So here you can see, during transcription, DNA is used as a template. It will form mRNA. Then that mRNA, with the help of ribosomes, it is going to form the protein. Clear bache? So that's how, right? That's how a protein will form. So they just separately mentioned it. Okay, but there is nothing to worry about. Okay, so once we'll complete transcription, translation, it is the part of protein biosynthesis only. Okay, so any doubt from syllabus? Yes? Do you have any doubt from syllabus? Okay, then now let's start the class. Let's start the topic. So basically, in this chapter, molecular basis of inheritance, this is the chapter name. Students, you know that in the genetics, one chapter is principles of inheritance and variation, another chapter is molecular basis of inheritance. Now when you talk about the inheritance, what exactly is the inheritance? It is the transmission, it is the process of transmission. Am I right? When I use the word inheritance, what is the meaning of inheritance? Inheritance means process, right? It means process of transmission, right? It is the process of transmission from right, the process of transmission of information or of characters from parents to offspring. That's what inheritance is. Am I right? That's what inheritance is. Am I right? Clear bache? Clear bache? So now what is the next point here, right? So in the chapter principles of inheritance and variation, we talk about the rules, right? That which rules are followed when it comes to the process of that transmission. But now what exactly is going to transmit from one generation to another? What exactly? We are saying the process of transmission of characters from parents to offspring, it is the inheritance. Okay, characters will pass, but what exactly is going to carry that character? right? Like we talk about the gene. What exactly is that gene? Gene is present on DNA, na? So here in this chapter we deal with the molecular ways, right? We talk about that biomolecule which will pass from one generation to another and which will carry the information. Clear, bache? So now Leharika, when we talk about that molecule, right, that molecule, so what is it? We know that we talk about the nucleic acids, isn't it? What do we discuss there? Nucleic acid. So can I ask you one question? Can you tell me nucleic acid, what are they? Are they bio micromolecules or are they bio macromolecules? Yes, students, what are they? Are they bio micromolecules or are they bio macromolecules? What are they? Anjani, Priya, Sahithi, everyone? And you have to tell me the reason as well. Yes? So it is basically, right, it is basically the bio macromolecule. Now why do we call it as a bio macromolecule? What is the reason behind? Right, macro, why macro? Because its molecular weight is above 10,000 Dalton. Okay, it is actually a polymer. These nucleic acids, they are actually, it is a polymer. Okay, and its molecular weight is above 10,000 Dalton. That's why we used to call it as, right, bache, that's why we used to say that it is a biomacromolecule. Now my second question is, obviously it is from biomolecules. Where are you going to find it? Are you going to find it in acid soluble fraction or in acid insoluble fraction? I really want to see, are you revising the chapter or not? Yes? Like where are you going to find it? Are you going to find it in acid soluble pool or in acid insoluble pool? Where are you going to find it? Yes? Acid insoluble pool. What is that acid insoluble pool? Is it the filtrate or is it the retentate? Noise, noise, noise. I like this discussion. Is it the filtrate or is it the retentate? Exactly, exactly. Hope you remember that trick. The trick is fast. What is the meaning of fast? It is F means, yes bache, F means filtrate, AS means acid soluble, okay, T stands for nothing. So filtrate is acid soluble, so you know that it's a biomacromolecule, so it will be there in the retentate, right bache, and that retentate is nothing, it is just the acid insoluble fraction. Okay, so start relating biology, right? Do not consider it as class 11th or 12th syllabus. Your all the concepts should be clear, right? So we know that nucleic acids, they are the one which will pass from one generation to another, and majorly it is the DNA. Okay, when it comes to RNA, earlier, because we have completed the evolution chapter, so we know it very well that the first genetic material was RNA, right? It was the RNA and then it evolved into DNA. Clear, bache? Because RNA used to serve other purposes as well. RNA carries the information, messenger RNA. RNA act like an adapter, transfer RNA. RNA is also used to make your ribosomes, right bache? So it is catalytic as well. Do you know na? RNA is catalytic as well. Ribozyme is the word. When RNA is acting like an enzyme, the word that we use is ribozyme. So that's what we know. Isn't it, Niharika, Anjani, Priya? Yes, bache. So now here you can see it is from NCERT that DNA and RNA, they are the two types of nucleic acids which are found in living system. And these nucleic acids, they behave like the genetic material. Clear, bache? They behave like the genetic material. So DNA means deoxyribonucleic acid, RNA means ribonucleic acid. So now if you want to understand the nucleic acids, we need to know about the nitrogenous bases in detail. Okay, so this is our next topic, nucleic acid. So as I said, what are they? They are the polymers. Yes, bache, what are they? They are the polymers. They are the polymers of nucleotides. Okay, right, polymers of nucleotide means many nucleotides, they are going to join and then they are going to form the nucleic acid. Okay, okay. So in simple words, what I just said, bache, what is a nucleic acid? Nucleic acid is a polymer of nucleotide, or you can simply say that it is a polynucleotide. It is a polynucleotide. That is the meaning of nucleic acid. This part clear, everyone? Yes, bache. This part clear? Okay. Now, what is the next point? If you want to understand the structure of nucleic acid, you should know what is a nucleotide, right? If you know what is a nucleotide, then obviously if you know the structure, then studying the nucleic acid is going to be easy for you. Now, when you talk about the nucleotide, there are three things, right? We will talk about the nitrogenous base. Okay, students, we are going to talk about, yes, first is nitrogenous base. We will talk about the sugar, and then we will talk about the phosphate. These are the three things we need to understand if we want to understand the nucleotide. Then we will talk about their bonding, right? But before that, let's talk about the structure of nitrogenous base in detail. Okay, okay, bache. So let's go. You should know the structure, bache, because it is given in your class 11 biomolecule book as well, and even it is given in your class 12th as well, okay, in molecular basis of inheritance chapter, plus it is also there in chemistry. So you should know about the structures. I'm not saying that you should remember, right, it, but at least by looking at the figure, right, you should know which one is adenine, which one is adenine, which one is cytosine, which one is thymine. Okay, so let's start the first thing, and that is nitrogenous bases. Please make the notes. Nitrogenous bases. So bache, it's very simple. Nitrogenous bases means they are something, they are the compounds which are having the nitrogen, right? They are the moieties which are having the nitrogen, obviously. So is a nitrogenous base a biomacromolecule or the biomicromolecule? Yes, bache, what is a nitrogenous base? Is it a biomicromolecule or is it a biomacromolecule? And guys, everyone, quickly hit the like button as well, and you have to stay with me till the end. All the topics are very important here. Here in the chapter molecular basis of inheritance, you cannot be selective, right? You cannot be selective. If you are actually targeting, right, 360 out of 360 marks, then you know that you cannot miss even a single line from this chapter. And today itself, right, in this particular class, we'll go as per NCERT. We are going to follow the same flow. Okay, there will be few mechanisms that I will explain, like that will be beyond NCERT, but ultimately it is the NCERT that we need to understand. So guys, everyone, speed up, and you have to stay with me. So show some energy, people, and please answer all the questions. Very good. Good evening, everyone. So what is the word here? The word here is nitrogenous bases. Nitrogenous bases. So definitely they have the nitrogen. And that nitrogen base, it is not individually a biomacromolecule. Its molecular weight is less. It is not a biomacromolecule, right? Which compounds are biomacromolecules? Those who are having molecular weight above 10,000 Dalton, and in this case it is going to be low. Okay. Okay. So nitrogenous bases. Here you will talk about the purines and the pyrimidines. What will you discuss? Purines and pyrimidines. Okay, so we have two tricks here. The first is Puga. Okay, there is one brand name, na, Puma. So instead of Puma, make it Puga, right? Puga. And here in pyrimidine, the trick is cut. What is the trick here? It is cut. So Puga. Pu means purines. What is the meaning of G? G means guanine. Okay. What is the meaning of A? A means adenine. Got it? A means adenine. Okay. So purines are guanine, adenine. And when you talk about the pyrimidines, it's cytosine, it's uracil, and it's thymine. It's cytosine, it's uracil, it's thymine. Right? These three are pyrimidine. So purines, pyrimidines. I'll tell you about their structure as well. One thing is purine, pyrimidine. And bache, guanine itself is denoted by G, adenine by A, cytosine by C, uracil by U, and thymine by T. Right? So you will use their first alphabet, first letter to denote them as well. So adenine, guanine, cytosine, uracil, and thymine. So purines and pyrimidines. So now what is the difference? See, one thing is for sure that both of them are going to have the nitrogen. So first of all, let's start with the purine. So we have two, right? One is your guanine, another one is your adenine. One is your guanine, another one is your adenine. So nin, guanine, adenine, 9. In their spellings, what will you see? 9. Okay. Okay, you can also recognize it like this. It is 9. So purines, what are they? It's a 9. They are 9-membered ring. It's a 9-membered ring. How many members are there in ring? 9-membered ring. Because bache, it is a nitrogenous base. Okay, it is a nitrogenous base. So in that ring at position 1, 3, 7, 9, nitrogen is present, right? In the ring, what I just said, it is a 9-membered ring. So in this particular ring at position 1, 3, 7 and 9, what are you going to get? Nitrogen, right? What are you going to get? Nitrogen. So the first difference clear? Yes, everyone, the first difference clear? Okay, so let's make the structure. Please make the structure. See, it is a 9-membered ring, right? It is a 9-membered ring. So this is nitrogen 1, means here in this ring, you are going to name it as number 1. This is number 2, number 3, it's 4, it's 5, 6, 7, 8 and 9. Okay, so total how many nitrogens are there? Total 4 nitrogens are there. 1, 2, 3 and 4. Okay, at 1, 3, 7 and 9. Clear? At 1, 3, 7 and 9. Okay, so 4 nitrogens are there. So it is a 9-membered ring. So when you look at this ring very carefully, right? See, look at this part. Okay, look at, yes, look at this part. It's a 6-membered ring. Only this portion. Is it a 6-membered ring? Yes, Vijay, Anjani, Niharika, Madara, Sahiti. Is it a 6-membered ring? Of course. 6-membered ring means it is a pyrimidine. But purine is a 9-membered ring. Pyrimidine is a 6-membered ring. It's a pyrimidine. What is it? It is a pyrimidine. So here you can see in this pyrimidine, 2 nitrogens are there, 4 carbon molecules are there. Right, 2 nitrogen, 4 carbon, and one ring is this one. Okay, this one, it is imidazole ring, right? You know it better. It is the imidazole ring. It is having 2 nitrogens but 3 carbons. So it's a 5-membered ring individually if you look at it. So can I say that in your purines, yes, can I say that in your purines, purine is made up of 1 pyrimidine ring and 1 imidazole ring. So pyrimidine and imidazole ring together, they are making the purines. Yes, bache, pyrimidine and imidazole ring together, they are making what? They are making the, yes, bache, they are making the, yes, purines. Clear? Clear, Priya? So you should know about their structure. Okay, you should know about their structure. So now look at this part. Purines. Okay, purines. So 1, 3, 7 and 9, and you can see that bache in the ring the alternate single double bond is there. Okay, here in this ring now, when you talk about the purines in this pyrimidine ring, alternate, yes, alternate single double bond is there. Double bond single, double bond single, double bond single, like this. That's what you need to remember. Here also double bond single and single here. Okay, okay, yes or no? Yes or no? Right? No, bache, this imidazole ring is like this only. Fine, it is like this only. You can even check, Aaron. So this is purine. So we have two purines. One is adenine, another is guanine. Do you know my way to remember this? Do you know my way to remember the rings? See, purine's 9-membered ring. I know it. I know the basic structure. I know its skeleton. Okay, I know its skeleton. Now the word is adenine and guanine. How can I differentiate? Let's say if in final NEET paper they are asking you a question, they are providing you 3 to 4 structures and they are asking you which one is adenine. The very first thing, Harshita, that you all can check is that is it 9-membered, or you can check, right, about that nitrogen. Is it present at 1, 3, 7 and 9? Yes. It is easy. Then if you need to find out which one is adenine, which one is guanine, then what you have to do, just look at it. Look at it. When bache it is adenine, right? When it is adenine. So here at 6th carbon you will see NH2 group. Okay, at 6th carbon you will see NH2 group. That's all. That's all. Okay, yes or no? Just a minute, students. Done, right? So in adenine, only at 6th position there will be amino group. Now how to differentiate adenine and guanine? Guanine, guanine, O, the sound of O is there. So in the case of guanine, at 6th position, C double bond O is present, right? This is my way to remember this structure. Okay, okay, so this is the basic structure, purines. Here you have adenine, right? So in adenine, right, Vardhan bache, in adenine what do you have? At 6th position NH2 group is there, right? NH2 group is there bache. And in guanine, it's guanine, O, double bond O at 6th position. And yes, there is one more amino group at 2nd position. So guanine is going to have this double bond O as well and NH2 as well, but in adenine only NH2 is there, right? Only NH2 is there, and rest everything is same like the basic structure. Okay, so that's how you can remember it. Is it easy or difficult? Do let me know in the chat section, students. Yes, Priya, do let me know in the chat sections. Is it easy or difficult? Is it easy or difficult? Easy na? It's very easy. It's very easy. Adenine and guanine. Now come to this part, pyrimidine. Okay. Next is pyrimidine. Right? It's pyrimidine. So when you talk about the pyrimidine, as I said, it's a 6-membered ring. Right? It's a 6-membered ring. 6 members are present. Right, bache? So 2 nitrogen and 4 carbon will be there. 2 nitrogen and 4 carbon. So that nitrogen is at 1 and 3. Right? The nitrogen is present at position 1 and 3. So here it was at 1379, but here it is at, yes bache, here it is at 1 and 3. Okay? It is at 1 and 3. Clear? Uh-oh. See, that's the basic structure. 1, 2, 3, 4, 5 and 6. Okay, 1, 2, 3, 4, 5 and 6. Again, alternate double bond and single bond will be there. Okay, alternate double bond and single bond will be there. Clear, bache? So that is pyrimidine. So now in the case of pyrimidine, we have 3 names. How many names do we have? We have 3 names here. C-U-T. What's that? That is C-U-T. So C stands for cytosine, U stands for uracil, right? And T stands for thymine. That is what we have. Okay, so now bache, one very important difference. It is also a difference in DNA and RNA, right? You know that we have 2 types of nucleic acid. One is DNA, one is RNA. Let me teach you the basics of this part and then we will also compare. But you can write down. In DNA, you have cytosine and thymine. Okay, right? Look at this Y. Same spellings, no? Y. And Y is there, and pyrimidine is also having Y, right? And when it comes to the RNA, in RNA, because it's uracil, R is there. So RNA is going to, just a minute, students. Okay, so R is going to be RNA and uracil. See, uracil is present in RNA, and other than uracil, it will have cytosine. Okay, so it is a previous year question. It's a previous year question, everyone, right? They ask you this thing, right, that which pyrimidines are present in DNA or RNA, or which purines are common to both DNA as well as RNA. So such questions can come. So when it comes to the purines, in RNA also adenine guanine is there, but when it comes to the pyrimidine, it's uracil and cytosine. Now when you talk about the DNA is having the guanine and adenine, along with that cytosine and thymine. So that's what you need to remember. Okay, that's what you need to remember. So now look at its structure. So as I said, 1, 2. So at 1 and 3, nitrogen is present. Basically 2 nitrogens are there in ring, so that's why it is 2n plus 4c. Okay, that's why it is 2n plus 4c. So that is what pyrimidine is. Okay, so now look at the structure of cytosine, uracil and thymine. Right, just look at the structure of cytosine, uracil and thymine. See bache, in the case of cytosine, right, even in cytosine, even in uracil, even in thymine, in all the 3 pyrimidines, at second carbon you will see the C double bond O. Am I right? This is what you are going to see. This is what you are going to see, Niharika. Just look at the structure. It's very easy to remember. It's very easy to remember the basic pyrimidine ring. Why? Because we are studying it from our class 11th. So I am assuming that you know it, right? And if you don't, please remember that. Please remember that. That's important. Okay. Second point is, now when you look at the cytosine, uracil and thymine, right? It's very simple. All three at carbon number 2, they are having C double bond O. Now when you look at the cytosine structure, at 4th carbon NH2, at 4th carbon C double bond O, C double bond O. Basically in uracil and thymine, when you look at the structure of uracil and thymine, it's almost same. The difference is that in thymine, right students, in thymine at 5th carbon methyl group is attached. Right, uracil and thymine, they are having same structure. The difference is that in thymine at carbon number 6 you will see the methyl group. What will you see, people? The methyl group. So that's why thymine is also known as 5-methyl uracil. Right, it's 5-methyl uracil. Right. So because of that, they are having a fight. Thymine is uracil is like, thymine, you cheated me, right? We were same. We both were same. But you acquired methyl group at your 5th carbon. So now I am not talking to you. That's why uracil is like that I will stay with RNA only. And thymine is like, okay, fine. If that's the case, I'll go for DNA. Okay, I'll go for DNA. So that's how I remember. Fine, that's how I remember. And I think even you can remember with the same trick. And in cytosine, here you have NH2 group. Right, so uracil, thymine, O, here NH2. By rest, all 3 are having carbon double bond O. Basically this carbonyl part, they are having C double bond O at their 2nd position. Understood? Clear? So the structure is clear? Structure is clear? Yes? Sure? Okay. So are you sure that if I will ask you the questions on the basis of structure, if I'll give you 2 to 3 structures and I'll ask you, tell me which one is purine, which one is pyrimidine. Can you do that? Yup. Can you do that? Okay. If I'll ask you that figure out which one is purine, which one is pyrimidine, can you? Okay, and if I'll ask you that figure out which one is adenine, which one is guanine, then which one is adenine, which one is guanine, then okay, then it's a very good thing. So again, for your quick revision, so do not get confused. When I was writing it, it was like this. So it's all same. So no need to get confused in the structures. Fine, no need to get confused in the structure. So it's it's 1, 2, 3, 4, 5 and 6. So basically at 6th position you are going to get NH2. Fine. Okay, so now let's talk about the sugar. Okay, right, let's talk about the sugar. So bache, what is a sugar? Is it a fat? Is it a protein? Tell me. What is a sugar? It's a carbohydrate. Thank God. Thank God. Seriously, thank God. So yes, you are right. Sugar is what? Sugar is a carbohydrate. Right? It's a carbohydrate having carbon, hydrogen, oxygen, of course. Okay, it's a carbohydrate. And you know that here we are going to talk about two types of sugar. One is going to be the ribose, another is going to be the deoxyribose. One is ribose, another is deoxyribose. So can you tell me, is it a monosaccharide, disaccharide, trisaccharide or tetrasaccharide? Yes, bache, Kalesh, Harshi. Is it a monosaccharide, disaccharide, trisaccharide or tetrasaccharide? What is it? Exactly, it's a monosaccharide. Okay, it is a monosaccharide. So if it is a monosaccharide, you are going to get it in acid soluble part, that is in the filtrate. That is in the filtrate. So it is a monosaccharide. Okay, so when you talk about the ribose, even the deoxyribose, bache, they are pentose. What are they? They are pentose. Pentose means 5 carbon. They are 5 carbon containing. Okay, 5 carbon containing. And in these monosaccharides, the functional group is aldehyde. That's why you call it as aldose also. If you understand this terminology, very good. Otherwise, do check my lecture right on this channel on biomolecules. Biomolecule chapter is literally very important. That's why, bache, when I provided you this video, na, this one, see this. See, array, wow. Okay, so this one, see, videos, 96 days biology plan. So here I clearly mentioned that you should revise biomolecules, molecular basis of inheritance all together. And here you can see another videos as well. Your Yava sir has posted this video for the physics. Please check it out, and bache, make sure that you know that topics. Okay, and yes, do check this video as well, forms other than NEET. That's also important. So now we are talking about the sugar, the monosaccharides. Okay, right. So monosaccharide means single sugar. It is okay, definitely it is a biomicromolecule. Now the point here is it's a pentose. Why pentose? Because it is having 5 carbon. And why aldose? Because it is having aldehyde as the functional group. Now my point is, if you remember that for monosaccharides, this is the general formula. Are you aware of it? For monosaccharides, yes bache, Madara, Shri, Likhita, Priya, Amrutha, this is the general formula for your monosaccharides. It's CnH2nON, right? It is CnH2nON. That's a general formula for monosaccharides, for single sugars. So here, if it is a pentose, so it simply means that N is equals to 5. N is equals to 5, isn't it? So it will be C5H 2 into 5 O5. Isn't it? C5H 2 into 5 O5. So C5H10 O5. It is C5H10 O5. Right? So this is the formula for the ribose. It's very simple. Okay. It is also a previous year question. It's a PYQ, the formula of ribose. So obviously ribose is a pentose. So if you don't remember the formula, you can use this. It is a general formula, CnH2nON. Okay, done bache. So it is the ribose. Now when you compare ribose and deoxyribose, without, D means without oxygen. So at second carbon, right, O is missing here. Like when you compare the structure of ribose and the deoxyribose, at second carbon O is 2' carbon, O is missing in deoxyribose, means it is less. So deoxyribose will have 1 oxygen less than that of ribose. So if I have to write down the general formula for deoxyribose, it is going to be this. right? Not the general formula, but the formula. If I have to write the formula for deoxyribose, so the formula will be this, na? One oxygen is less, right? So remember, it is an exception. Okay, deoxyribose is an exception. It is a monosaccharide, but it does not follow general formula. Another previous year question. Okay, it's a monosaccharide, but it doesn't follow general formula, right? Right? That's a MCQ. Clear, bache? Ribose and deoxyribose part clear? Okay. So now let's look at their structures. So it's a furanose. Am I right? It's a furanose. Let's revise the biochemistry also. Okay, so it's a furanose. Why furanose? Because here in this ring you have one oxygen, right? One oxygen and 4 carbon. Okay, so it's a furanose. I hope you remember. So basically we are revising biomolecule as well. So it's carbon number 1, it's carbon number 2, it's carbon number 3, it's carbon number 4, and it is the carbon number 5. Okay, 1, 2, 3, 4, 5. Yes, everyone, 1, 2, 3, 4, 5. Here also, this is carbon number 1, carbon number 2, carbon number 3, carbon number 4, and carbon number 5. That's what we have. So, bache, it is ribose sugar. Which sugar it is? It is ribose sugar. And this one is deoxyribose. So, how can I say that? Because at second carbon, the oxygen is missing. So, you have to be very specific here, bache. You cannot mention third carbon, you cannot mention fourth carbon, you have to mention Likita second carbon only. Okay, you have to mention second carbon only. Understood? Understood? Done? So ribose and deoxyribose. Now see, do you remember two things, alpha monosaccharides or beta monosaccharides? Yes, alpha monosaccharides and beta monosaccharides. Do you remember that part? Sahiti, Niharika, Madara, Samriya, Harshi, Priya. Yes, alpha and beta. So A for alpha, A for above, B for beta, B for below. A for alpha, A for above, B for beta, B for below. So if your hydrogen is above, obviously you always talk about the carbon number 1. Here your hydrogen is below, so obviously it is the beta pentose, it is the beta ribose. Okay, because hydrogen is below. So if it is above, if H is above, it is going to be your alpha sugars. If your H is below, it is going to be your beta sugars. We talk about now alpha glucose, beta glucose, so that is the difference, right? That is the difference. So now you know the structure of nitrogenous bases, right? You know the structure of sugar. Now the third thing that you need to understand is the phosphate. The third thing that you need to understand is the phosphate. Okay, see, basically you are going to talk about the phosphoric acid here, right? What are you going to discuss? Phosphoric acid. Which one is the phosphoric acid? This one. This one is the phosphoric acid. So in DNA it is the phosphoric acid which is used, not the phosphorus, right? You remember now, you have another acid also which is known as phosphorus. One is phosphoric acid, another is phosphorus acid. Remember, one is phosphoric acid, Leharika, right? Another is phosphorus acid. So please keep it in your mind. It is not the phosphorus acid which is making the DNA. It is the phosphoric acid. This is the phosphoric acid, right? Where it is having H3, right? H3PO4. It is H3PO4. Okay, what is it? It is H3PO4. Understood? It is H3PO4. Yes, oxytocin. Is it clear? So you remember in your NEET 2023 it was a PYQ, but yes, in chemistry it was a PYQ of chemistry. Do you remember this? Done. So do not get confused. In DNA it is the phosphoric acid. And how can you remember it? Again I have a trick. So DNA is a nucleic acid. Yes bache, DNA is a nucleic acid. Harshi, DNA is a nucleic acid. IC. IC. So same way, phosphoric acid. IC. That's how I remember. Okay, that's how I remember. And this phosphorus acid is what? It is P double bond O, OH, OH and H. Okay, that is your phosphorus acid. Fine. So it is the phosphoric acid. And when do we say it is a obviously, and if it is O negative, O negative, O negative, it is the ionic form. You can use the word phosphate. Fine, Kiran, you can use the word phosphate. Is it clear? So that's what you have to remember. So in DNA it is the phosphoric acid, and this acid is going to give acidic properties to DNA. And because of this phosphoric acid, obviously it is acid, that's why DNA is negatively charged. Fine, that's why DNA is negatively charged. So DNA is negatively charged. Why? Because of the presence of acid. Which acid it is? Phosphoric acid. So when you talk about its ionic form, it is the phosphate. So that's important. Fine, that's important. Clear? So now the next thing. Now, before understanding the nucleotides, you should know about the nucleoside. About the nucleoside. But everything is important. Please pay attention. Yes. Please pay attention. Next is what, Niharika? It's nucleoside. So N means nitrogenous base. N means nitrogenous base. S means sugar. So nitrogenous base plus sugar, it makes nucleoside. When a nitrogenous base, Girija, when it joins with the sugar, you are going to call that structure as nucleoside. It's not tied, it's side. So in the final paper, they even ask the differences in between nucleoside and nucleotide. Clear? Clear? So another important question is, which bond is going to join them together? It is N-glycosidic bond. Right? It is N-glycosidic bond. Clear? Which bond it is? It is N-glycosidic bond. Clear, bache? Sure. So you should know about the bonding. You remember in NCERT, right? In the structure of DNA, they discuss the structure of your, what we call it, the 3,5 phosphodiester bond. We have to discuss that. So you should know about it. So tell me which sugar it is. Is it a ribose sugar or a deoxyribose sugar? Look at the structure and tell me. Yes, which sugar it is? Which sugar it is? Okay, how can you say that it's a ribose sugar? Yes, bache? Yes, this OH. Now sugar is sweet, so obviously your nitrogenous bases are going to pair with it, right? Your nitrogenous bases are going to pair with it, right? Okay. So is it a purine or pyrimidine? Is it a purine or pyrimidine? Is it a purine or pyrimidine? Purine, thank God. So 1, 2, 3, 4, 5, 6, 7, 8 and 9. Right? 1, 2, 3, 4, 5, 6, 7, 8 and 9. So now bache, this is the sugar. So how that bonding will be there? The ninth, because it is a purine, right? In the case of purine, the 9th nitrogen, right? The nitrogen which is present at 9th position. Okay, obviously it is also having the hydrogen. It is also having the hydrogen. Look at the structure now. Right now I didn't specify it. Let's look at the structure of your adenine. In the adenine, right, at 6th position CH2. Here we need to satisfy the valency also. So NH is present, right? NH is present. Am I right? So at 9th, right, at 9th carbon, you know that this hydrogen is there. So we are going to make which bond? Glycosidic bond. So you know that it is the glycosidic bond which formed by the dehydration. How that bond will form, bache? It will form by when there will be the dehydration. The water will release. So H2O, it will be released. Yes, H2O, it will be released here. Yes or no? Leharika, Samriya, Sahiti. H2O, water will be released here. Am I right? Water will be released here. Am I right? So now what is going to happen after that when water is released? Obviously the nitrogen of the, right, this will directly pair with this carbon. Okay, this nitrogen will directly pair with this carbon, and now it is a nucleoside. It is a nucleoside. So which bond do they have? They have N-glycosidic bond. Why do we call it as a N-glycosidic bond? Because nitrogen is involved in bond formation, right? Here one carbon, one nitrogen. That's why it is the N-glycosidic bond. Is it clear? It is a nucleoside. Now, bache, the nomenclature. The another important thing is nomenclature. What is it? Another important thing is nomenclature, naming. Now adenine is a nitrogenous base. Ribose is a sugar. When you will join them together, you will get a nucleoside, right, Leharika, Sahiti? Yes, you are going to get a nucleoside. So adenine plus ribose, it will be adenosine. Hope you know this word, adenosine. So if adenine is written, it's a nitrogenous base. If adenosine is written, it's a nucleoside. It is a nucleoside. Same way, bache, if adenine plus deoxyribose, if the sugar is deoxyribose, then it will become deoxyadenosine. It will become deoxyadenosine. Then if it is a, let's pick up uracil. Okay, if it is uracil plus ribose, you know that it is going to be uracil plus ribose only, because uracil is present in RNA. RNA is having the ribose sugar. So now it is uridine. So if uridine is written, uridine is a nucleoside. Uracil is a nitrogenous base. Now thymine plus deoxyribose, right? Because it is present in DNA only. So it will be thymidine. It will be thymidine. What's that? It will be thymidine. Understood? Clear, bache? So the nomenclature is important. Fine, nomenclature is important. So deoxyadenosine means the sugar is deoxyribose. Deoxyguanosine, deoxycytidine, deoxythymidine, or you can simply write it as thymidine, right? Okay, and uridine means RNA, uracil plus ribose. So that's how you have to remember. Okay, so if sugar will be ribose, then it will be cytidine only. The sugar will be ribose, it will be guanosine only. So the nomenclature is important. The question will come from nomenclature. Now the next thing is, yes bache, the next thing is nucleotide. Now the word is nucleotide. T means 3. T means 3, means 3 things are there, right? Already we know that nitrogenous base and sugar, they will join. So here there will be the addition of phosphate as well. Here there will be the addition of phosphate as well. So nitrogenous base, sugar plus phosphate, together they are going to make one nucleotide. What will it make, bache? It will make one nucleotide. So nitrogenous base plus sugar, here they will join together with the help of glycosidic bond. Am I right? They'll join together with the help of glycosidic bond. Am I right, Priya? And the sugar and phosphate, they will have phosphoester bond, right? They will have phosphoester bond, right? Yes, bache, they will have phosphoester bond. Clear? So This part clear? Tell me. This part clear? So here I'll add one thing. See, when N-glycosidic bond is in between sugar and pyrimidine, if it is in between sugar and purine, if nitrogenous base is purine, then nitrogen at 9th position is involved in bonding. Okay. And bache, when N-glycosidic bond is in between sugar and purine, then nitrogen at 9th position is involved in bonding. Okay, but right. So this is what you need to remember. Okay, and when it is the purine, then when it is the purine, then bond is in between. Then bond is in between first carbon of sugar and first nitrogen of pyrimidine. Okay, then there will be the first nitrogen of pyrimidine and first carbon, right? First carbon here, when it is in between sugar and purine, then N at 9th position is involved in bonding of purine is involved in bonding, and first carbon of sugar is involved. Understood? Right? Understood? Sure? Is it clear? Okay, so now let's talk about the bonding in the case of a nucleotide. So bache, please understand the bonding in the case of a nucleotide, because then I will tell you the bonding in between two nucleotides. So when you will understand this bonding, you will get to know about that 3-5- phosphodiester bond, right? Many times students, they get confused when it is the phosphoester bond or the phosphodiester bond. So please listen to this part, and then the structure of DNA will be very easy for you. So up to this part, if there is any doubt, do let me know, students. Yes, I know in biochemistry, many students, they find it difficult. They find it difficult to remember the structure, the bondings, but trust me, you just need to understand it once, right? So please today be patient, and today just listen to me. Okay, if there will be any doubt, you are allowed to ask me the questions, but yeah, you have to stay with me till the end. Fine, we'll go slow. If there is any topic where majority of students where they want me to, right, teach it slowly, I'll go slow. Okay, if there is any doubt, I will explain that too, but listen to me carefully, and trust me, this chapter is easy. This chapter is easy. It's a concept based chapter. Fine. So always remember, sugar is sweet, right? So all of them, the nitrogenous base, okay, even the nitrogenous base, and even your, what we call it, phosphate, it wants to join here with the sugar only. Clear? So now tell me which sugar it is. Which sugar it is? Yes, it is deoxyribose, and this is the carbon one, and here it will join with the nitrogenous base. So this is a nucleoside. Is that clear? This is a nucleoside. Is that clear? Do I need to show that bonding again? No, na? Do I need to show that bonding again? I don't think there is a need. So now come to the phosphate. So it is P double bond O, OH, OH and OH. This is what we have, right? This is the phosphoric acid. Yes, bache, this is the phosphoric acid. So now what is going to happen? The fifth carbon of sugar, okay, the fifth carbon of sugar is going to form a bond with this phosphoric acid, and again, right, this is the ester bond, bache. So again, what is going to happen? There will be the removal of water. So after water removal, we are going to get phosphoester bond, right? We are going to get phosphoester bond. So when it is a nucleotide, Okay, when it is a nucleotide, so in a nucleotide there will be one N-glycosidic bond and one phosphoester bond, one N-glycosidic bond and one phosphoester bond. So look at this part first. Okay, then this one. So please draw the structure. Right, so what I just said, that this fifth carbon is involved in bonding, right? So here OH will be removed. Okay, so we are left with this now. Am I right? Yes. Am I right? Actually it is. Yes. Am I right? This bonding part clear? Sure? Sure. Of course. This is the phosphoester bond. This is the phosphoester bond. Okay. So again, please see this. Sugar is sweet. Right? So even the nitrogenous base, even the phosphate, they want to join sugar. So the first carbon of the sugar is going to form the bond with the nitrogenous base. Fifth carbon of sugar is going to form bond with the phosphate, right? So there will be the formation of ester bond. So it is phosphoester. Why? Because see, normally this is what your ester bond is, right? This is what your ester bond is. Yes or no? This is what your ester bond is. C double bond OO. Right, but here instead of C, it is P double bond O. That's why you used to call it as, so that's why you call it as phosphoester bond. Okay, that's why you are calling it as phosphoester bond. Understood? Sure? Fine? Okay, so that's how you are going to get the nucleotide. So please look at this bonding part. Right, look at this bonding part. So here, right, sugar, the first carbon. And because it is a purine, so 9th nitrogen of purine. When it is a nucleotide, that's how the phosphate is going to join. Fine, that's how the phosphate is going to join. Fine. So here obviously it is not just one phosphate, one more phosphate is there, we'll come to this. Okay, so that's the structure. If there is any doubt, do let me know. I hope it's clear now. You can see what is a nucleoside, what is a nucleotide. So you need to remember the nomenclature as well. So students, see, it's very clear. If adenine plus ribose, if it is giving us adenosine, which is a nucleoside. Now in that adenosine, what we just added? We just added one phosphate to make it nucleotide. Yes, Sabha? Yes, Likhita? See, nitrogenous base plus sugar, it is a nucleoside. Nitrogenous base plus sugar, it is a nucleoside. Adenine plus ribose, it is adenosine. Right, it is adenosine. Now we have added one phosphate, only a single phosphate there. So obviously adenosine monophosphate. Adenosine monophosphate means it is a nucleotide. Am I right? Adenosine monophosphate means it is a nucleotide. Am I right? Yes? If it is adenosine, it means it's a nucleoside. If it is adenosine monophosphate, it is a nucleotide. So nomenclature is also important. So adenosine monophosphate is also known as adenylic acid. It is also known as adenylic acid. Clear? It is also known as adenylic acid. Like for an example, if it is guanosine monophosphate, again it means it's a nucleotide, and you can also call it as guanylic acid. It's one and the same thing. Fine, it's same. Okay, you call it as guanylic acid. So see this, deoxyadenylic acid or deoxyadenosine monophosphate, it's same. Deoxyguanylic acid, deoxyguanosine monophosphate, it's same. Deoxycytidilic acid or deoxycytidine monophosphate, it's same. Is that clear? Yes, is that clear? So the nomenclature is important. Okay, the nomenclature is important. So this is all about the bonding, right bache? So quickly tell me, which bonds are you going to see in the nucleotide? Which bonds are you going to see in the nucleotides? Quick. Which bonds are you going to see in the nucleotide? Bache, see, if you people will like Mr. Papa or Harsha, and Princess, bache, I'll block you guys. Okay, you just have 2 or 3 minutes. If you will not stop chatting, I'll block you. Yes, Amriya, it is the N-glycosidic bond and the phosphoester bond which is present in a nucleotide. And what about polynucleotide chain? What about polynucleotide chain? That's what I just said now, that if you really want to understand the structure of, yes, if you really want to understand the structure of what? Right, if you really want to understand the structure of nucleic acid, so you should know about the nucleotide first, because nucleic acid is formed by the polymerization of many nucleotides. Okay, so if I have to join, yes, so how can I make a polynucleotide chain? See, I know nucleotide means sugar, nitrogenous base, phosphate, right? Another next nucleotide is sugar, nitrogenous base, phosphate. Please look at the structure: sugar, nitrogenous base, phosphate. Clear bache? Sugar, nitrogenous base, phosphate, right? So these are the nucleotides that we have. These are the Niharika nucleotides that we have. So if I have to make a polynucleotide chain, so I have to join these nucleotides. Okay, so I have to join this first one with the second one, with the third one, with the fourth one. So when you look at it, how are we going to join, bache? The sugar, right? The sugar of first nucleotide. The sugar of first nucleotide will form bond with the phosphate of next nucleotide. The sugar of first nucleotide will form bond with the phosphate of next nucleotide, like this, like this, like this, right? Can you see that now, Priya? Can you see that in a polynucleotide chain, somewhere we see a sugar phosphate backbone? Not somewhere, actually we see this sugar phosphate backbone. Look at this part: sugar, nitrogenous base, phosphate. Sugar, nitrogenous base, phosphate. So we have to join one nucleotide with the next one, So the sugar of first nucleotide will form the phosphate of next nucleotide. This is how the sugar phosphate backbone will form. And when you look at the bases are there in center. They are kind of forwarded. They are present like this, right? Is it a polynucleotide chain? Is it a polynucleotide chain? Yes, is it a polynucleotide chain? Sure. Okay, so now look at the bonding part. Fine, let's talk about the bonding part, which I am going to cover very important aspects, very important topics here. Please listen to me carefully. Is it clear? Sure. So this is basically the 5 dash carbon. This is the 1 dash. You can also call it as 1 prime, right? Let's say it is a deoxyribose sugar. Sorry. Okay, first carbon, second, third, fourth and fifth. Am I right? First, second, third, fourth and fifth. First, second, third, fourth and the fifth carbon, right? Is it a nucleotide? Yes, Bhumika. Is it a nucleotide? Is it a nucleotide, everyone? Yes, right? So the next nucleotide, okay, okay, wait. So this one is your first nucleotide, okay, this one is your second nucleotide. Please look at the structure and do let me know if there is any mistake. Yes, Blue, Ramesh, Ujay, please look at the structure and do let me know if there is any mistake. Both are nucleotides. Both are nucleotides. Yes, both are nucleotides, yes or no? Of course, yes, right? So this is the first nucleotide. So the 3-OH, right? 3-OH of first nucleotide. 3-OH of first nucleotide. Now, this OH here, okay, it is involved in the bond formation with the next phosphate, right? If let's say if I'm not writing it in the ionic form, you know what is going to be there? OH, OH and OH. So, yes, OH, OH and OH will be there. Yes or no? Yes or no? So again, what is going to happen? The water will come out. Minus H2O. Obviously, which bond is going to form here? Which bond is going to form here? Yes, students, do let me know which bond is going to form here. The another ester bond, right? It is going to be the another ester bond. Am I right or not? 3-OH of first nucleotide and 5-phosphate of next nucleotide. They will form bond. Right? They are going to form that ester bond. Right? They are going to form ester bond. Am I right? So now, because see here, is it a ester bond? No, it is a phosphodiester bond. Right? See, one bond here, one bond here. So it is a phosphodiester bond. Clear, bache? So it is a phosphodiester bond. It's 3-5-phosphodiester bond. Understood? Right? And why 3-5? Because the third carbon of first sugar, the OH group of third carbon of first sugar is going to form the bond with the phosphate of the fifth carbon of the next sugar. So that's why it is 3-5. The 3- of this sugar, the 5- of this sugar, they are going to link with the ester bond. So it's a phosphodiester bond. It is a phosphodiester bond. Clear? So bache, it is a previous year question. Sometimes we make mistakes. So if it is a one nucleotide, if it is just a nucleotide, then it is phosphoester bond. If it is a dinucleotide, or you can say that if it is a polynucleotide chain, okay, then it is going to be phosphodiester bond. Otherwise it is phosphoester bond only. Clear? Clear? Sure? Sure? So today Are you feeling like it is as a like it's a biology class? Huh? Is it a biology class today? Nah, it's a biochemistry class. It's a biochemistry class. No, that's not boring. That's very interesting. That's not boring. That's interesting, and it's not at all confusing if you understand the structures individually, right? How do you manage chemistry? How do you manage chemistry? Like in chemistry, bonding is there, different types of bonds are there, that lone pair, this pi bond, this bond, that bond. And here though we need to talk about only two bonds, basically three bonds: hydrogen bond, phosphoester or diester bond, and your N-glycosidic bond. So if you know the structure, then it's not difficult. Okay. If you don't know the structure, yes, definitely then it is difficult. Clear? So can we revise it? Can we revise it? So we started the story from the nucleic acids. Okay. Let's revise everything. So we started the story with the nucleic acid. So we know that how many types of nucleic acids are there. I know you know the answer. How many types of nucleic acids are there? Two, right? One is DNA, another one is RNA. One is DNA, another one is RNA. DNA, RNA, DNA, D, double stranded. It's deoxyribonucleic acid. So the sugar is deoxyribose. And which bases are there in DNA? Adenine, guanine, cytosine, thymine. Now when you talk about the RNA, RNA is also a genetic material, but in viruses. Okay, and mainly when you talk about the RNA, students, it is single stranded and it used to play another roles, okay, like messenger RNA, transfer RNA, you know about it. So RNA is having ribose sugar, RNA is having adenine, guanine, cytosine, but at the place of thymine, uracil is there in RNA. At the place of thymine, uracil is there in RNA. So if we need to understand the nucleic acid, the structure of nucleic acid, we should know about the nucleotide. Why? Because nucleic acid is a polynucleotide chain, right? Nucleic acid is a polynucleotide chain. Now move to the next part. Clear, bache? So nucleotide is made up of three things. It's nitrogenous base, sugar, and the phosphate. So when it comes to the nitrogenous base, we have purines, we have pyrimidines. Am I right? We have purines, we have pyrimidines, and even we have the tricks also. One is your puga, another is your cut, right? Clear, bache? So when you talk about the purines, it's a 9-membered ring, one pyrimidine ring plus one imidazole ring. Okay, so at position 1, 3, 7 and 9, nitrogen is present. At position 1, 3, 7 and 9, nitrogen is present, right? You can just look at the spellings also. Guanine, adenine, nin, 9 is the word there. 9. So 9-membered ring it is. Clear? Now when you talk about the pyrimidine, pyrimidine is a 6-membered ring. It is a 6-membered ring. Clear, bache? Clear, bache? So position 1, 3. Position 1, 3. Right? Right? Now look at the structure also. So cytosine, uracil, thymine. Thymine is also known as 5-methyl uracil. Why? Because in thymine at 5th position, methyl group is there. Rest the structure is same, like structure is similar to the uracil. Okay. Okay. So this is about the structures. Now then we discuss the sugar, which is the carbohydrate, and here in both the cases, ribose as well as deoxyribose, we have pentose sugar. Leharika, which sugar do we have? Sabha, Leharika, Priya, yes, Laya, Anjani, which sugar do we have? We have pentose sugar. Pentose means 5 carbons. 5 carbons. So C5 it is. C5 it is, and this is the general formula: CN, H2N, ON, C5H. H10O5. That's what we have. Okay, so deoxyribose, it is an exception. It doesn't follow the general formula for the monosaccharides, but yeah, it's still a monosaccharide. Clear? It is still a monosaccharide. Now look at the sugars and tell me the differences, right? Just look at the structure and please let me know the differences. Look at the structure and please let me know the differences. Okay, good, very good. So next is phosphate. You know that it is the phosphoric acid and this is the formula. So now we have to understand the nucleosides. So nucleoside, it is N nitrogenous base, S sugar, right? N nitrogenous base, S sugar. So when nitrogenous base and sugar, they join, they are going to form the nucleoside, and N glycosidic bond is the one which is going to link them. So how that bond will form? The first carbon of sugar is involved in bonding, and when it is a purine, the 9th nitrogen of purine is involved in bonding. Clear? So dehydration will be there and the bond formation will be there. So if it is pyrimidine, yes bache, awkward potato, if it is pyrimidine instead of purine, then the bonding is in between. Can you answer this question? Then the bonding is in between. Quick students. Then the bonding is in between the first carbon of the sugar and the first nitrogen of the nitrogenous base. Very good, Krutika, excellent. Now the third thing is nucleotide. So nucleotide is having nitrogenous base plus sugar plus phosphate. So three things are there. So sugar is sweet, right? Sugar is sweet. That's why even the nitrogenous base, even the phosphate, they both want to join with that sugar. So in the case of nitrogenous base and sugar, you have N glycosidic bond, right? It is going to link nitrogenous base and sugar, and in case of sugar and phosphate, it is the phosphoester bond. It is the phosphoester bond. Clear, bache? Now when you look at this part, so sugar, nitrogenous base, you know about this bonding, right? You all know about this bonding, right? It is N glycosidic bond. So now the fifth carbon of your sugar, right? It is going to form the phosphoester bond with this phosphoric acid. Clear, bache? With this phosphoric acid. Now when you move to the dinucleotide chain, okay, when you move to the dinucleotide chain, so see this, the condensation. Look at this reaction. So here, nitrogenous base, see, it's a ribose sugar, right? And here the fifth carbon, so CH2O, and this is phosphoester bond. So here just look at it, bache, it is the next nucleotide. So 3' OH, right? OH means this hydroxyl of this third carbon, it is going to react with the phosphate of the next nucleotide, and you know that again the chemical reaction will be there. And now which bond is there? It is the, yes bache, which bond is there? It is the phosphodiester bond. It is the phosphodiester bond. Any doubt? Yes, Priya, Niharika, any doubt? Any doubt? So now I hope you know this thing. I hope you know this thing, that whenever we talk about the, yes, whenever we talk about the synthesis, be it the synthesis of RNA or the DNA, we always used to say the synthesis is in 5' to 3' direction, right? That's how we use this arrow, right? That synthesis is always in 5' to 3' direction. It is another important MCQ. Okay, it is another important MCQ, that whenever we talk about the synthesis, it is going to be in 5' to 3' direction, right? 5' to 3' direction, right? Even if it is the structure, even if it is the synthesis of DNA, it is also same, 5' to 3' direction. Even if it is the synthesis of RNA, it is also going to be in same direction, 5' to 3' direction. Always. Why? Look at this nucleotide chain. When you talk about the first nucleotide, don't you think its 5' end is free? Its phosphate is free. If I talk about first nucleotide, it is not having, at fifth carbon, it is having phosphoester bond, not the phosphodiester bond. Look at this. It can be asked as a question. When you look at the polynucleotide chain, see, now we join two nucleotides. We can add one more. We can add one more. We can add one more. You know that. Right? For the formation of a chain, we have to add more. Spandana, we have to add more. We have to add more. We have to add more. That's what we know. So now when you look at the structure of the first nucleotide, right, at the fifth carbon of the first nucleotide, phosphoester bond is there. It is not phosphodiester. But when you talk about the next nucleotide, the fifth carbon of next nucleotide, it is having phosphodiester bond. It is having phosphodiester bond. So pay attention, please, kindly pay attention. Each and everything written here is very important, right? It is very important, and no one is going to emphasize such points in a one shot. So that's why we always used to say it's a detailed one shot. Look at this. This is one nucleotide, this is next. This is one nucleotide, this is next. Okay. When you look at the first nucleotide, 5' carbon is having phosphoester bond. You have to tell me yes or no. You have to tell me yes or no. Forget about the condensation. You look at the first nucleotide, at its 5' carbon, we have the phosphoester bond, yes or no? Yes, we have the phosphoester bond. Now look at the next nucleotide. At its 5th carbon, do we have the phosphoester bond? Yes, we have the phosphoester bond. Now we are, Ramesh bache, now we are talking about the condensation. We are talking about joining these two nucleotides together. Now we want to join these nucleotides together. Now we want to make a polynucleotide chain. Okay, now we want to make a polynucleotide chain. So what is going to happen here? What is going to happen here? Just look at this point, bache. Look at this point. This is the first nucleotide. The 3rd carbon, the 3' carbon, the hydroxyl group of 3' carbon of this sugar, of first sugar, it will form bond with the phosphate of the next sugar. Am I right? The OH group of this first nucleotide sugar is going to form the bond with the phosphate of the next nucleotide's sugar. Right, so they will form the bond. You know that it is the phosphodiester bond, right? It is the phosphodiester bond. So now I'm showing you this chain. I'm showing you this chain. When you look at the starting of this chain, the 5' carbon, is it free? Is it free means, is it involved in bonding with something else? No, 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 not at all. This 5th carbon is having free phosphate group. This 5th carbon is having free phosphate group. I'm using P for denoting phosphate as of now. I know single P is phosphorus. No, I'm saying phosphate. But as of now, you please remember this. Okay. So when you look at this polynucleotide chain, imagine we are synthesizing a polynucleotide chain. Right? Imagine we are synthesizing a polynucleotide chain. Okay, so when you look at this chain, the 5th carbon, it is having free phosphate. It is having free phosphate. Yes, of course it is having. See, it is just having this phosphate group attached to the 5th carbon by phosphoester bond. Now look at the next nucleotide. In between, 3' carbon of first, 5' carbon of next. Phosphodiester bond is there? Yes, ma'am. Phosphodiester bond is there. So here this 5th carbon is not free. The phosphate here is not free. It is involved in bonding. It is involved in bonding, Leharika. Only this 5' carbon, its phosphate is free. Right? Its phosphate is free. So now let's say you have added more bases. You have added more bases. Right? This one is your first nucleotide. This one is your last nucleotide. Right, this one is your last nucleotide. So in this last nucleotide, your phosphate is involved in bonding, but the 3' OH group is free. But the OH group is free. Yes, bache, but the OH group is free. Yes, so we always used to say the synthesis is in 5' to 3' direction, right? The 5' to 3' direction, and 5' is having free phosphate group, 3' is having free hydroxyl group. This is the language of your NCERT, Sabha, right? Sabha bache, it is the language of your NCERT. 5' is having free phosphate group, right? 5' end is having free phosphate group, and 3' end is having free hydroxyl group. Right, it is having free hydroxyl group. Clear, bache? Right, what is the meaning of Nandani? Free. 3' OH means it is free for the bonding. It is not yet involved in bonding. Clear? So look at this. Let's imagine this is a long polynucleotide chain. First base, second base, you are adding more and more. At the end, this 3' OH will be free. Am I right? 3-OH will be free. So that's why we say 5' is having free phosphate, 3' is having free OH. If you can remember it, very good. If you cannot remember, you cram it. It's your wish, but you should know about it. Look at this polynucleotide chain. See, 5' end pe we show the phosphate. Okay, 3' end the free hydroxyl. That's what I'm saying. If let's say they have given you the diagrams, in that diagrams if they have mentioned 5' is having OH, it's incorrect. If they have mentioned 3' is having phosphate, it's incorrect. Okay, okay. So 5' end is having free phosphate, 3' end is having free hydroxyl. So see, sugar, nitrogenous base, right? Sugar, nitrogenous base. This is the phosphate here. This is the phosphodiester bond which is linking one nucleotide to the another, right? This is the phosphodiester bond which is linking one nucleotide to the another. So now can I ask you one question? Can I ask you one question? Let's say this diagram is there in the paper, right? Let's say diagram is there in the paper. Now they marked it as A, right? Right, it is clearly mentioned that it's a polynucleotide chain. They marked it as point A, okay, or they marked it as point B, okay. So they are asking you about the bonding. Which bond is present here? Tell me. Which bond is present here? Tell me. At point A or at point B? At point A or at point B? See, some students are mentioning this A as phosphodiester. No, this is the first nucleotide. It is just a single ester bond. So here it will be phosphoester bond only. Now when you look at this part, it is the yes bache, it is the N-glycosidic bond. It is the N-glycosidic bond. Now what about this bond? What about this bond? This is going to be phosphodiester bond. Understood? Sure? Okay, very good. So now let's talk about the structure of DNA. Fine. So DNA is what? DNA is a polynucleotide chain. Okay, so D for DNA, D for double stranded, right? D for DNA, D for double stranded. Clear bache? So DNA, as I said, it's a long polymer of deoxyribonucleotides. So instead of deoxyribose, if in your final exam, if in one MCQ they have mentioned the ribonucleotides, is it going to be correct or incorrect? Yes, it should be deoxyribonucleotides or ribonucleotides. It should be deoxyribonucleotides. Okay, so the length of the DNA is usually defined as the number of nucleotides or a pair of nucleotide referred to as base pair. But we will talk about the pairing also. We will talk about the Chargaff rule, Arvind-Chargaff rule. But I hope you know that there is a complementarity in DNA chain. Adenine is also always going to pair with thymine, and cytosine is always going to pair with guanine. So it will pair with two hydrogen bonds are going to join adenine with thymine, and 3 hydrogen bonds are going to join, right, cytosine and guanine. Is that clear? So 2 hydrogen bonds and 3 hydrogen bonds. That's the point. Understood? That's the point. Okay. So DNA is a long polymer of deoxyribonucleotides. So length depends upon the number of nucleotides. So this is another important MCQ. Please mark it. Right, so number of nucleotides are going to decide the length of the DNA. So this also is the characteristic of an organism, obviously. Now see, bacteriophage, known as this, what is this, 5, right? 5 into 174 has 5386 nucleotides. But this data is important, please note down. Yes, this data is important. MCQ can come, right? MCQ can come from this part, so please note down. Okay, so you should know about this data. You should know about the number of bases as well. Fine. Okay. Sure. Sure. And next is bacteriophage lambda. It is having 48,502 base pairs. They are talking about the base pairs, not the individually the bases. Another important question. See bache, although we need to discuss the DNA structure, we need to talk about the bases, but remember, when the word is base pair, that's the point, right? We are talking about a pair. We are talking about a pair, right? If they simply mention the nucleotides, right? So here, this bacteriophage 5 into 174, it is having 5386 nucleotide. So they are talking about single bases. It's not the base pair, it's the single base. Okay, it is not the base pair, it's the single base. And this particular bacteriophage is having single stranded DNA. Okay, and that DNA, obviously, because it is a virus, it's a linear DNA. Fine, it's a linear DNA. You can note down this information. Okay, you can note down this information. Fine. And now see here in this case, in the case of this bacteriophage lambda, 4852 base pairs are there. Now the word is not nucleotide. Now the word is not single base. It is base pair. So please pay attention to such things. Okay. So sometimes we just focus on the number that it is 48502. Then okay, my question is correct. No. Is it a base pair or is it a nucleotide? Right. You need to focus on that. You need to focus on that as well. So this bacteriophage lambda, it is also a double stranded. Yes, it is also having double stranded DNA. Okay, but again the DNA is going to be linear. Then Escherichia coli, that is your E. coli, it is having 4.6 into 10 raised to power 6 base pairs. Okay, and haploid content of human, it is having 3.3 into 10 raised to power 9 base pair. So it is the haploid content. So what about the diploid content of humans, bache? It will be 6 into 6, 10 raised to power 9 base pair when it is the diploid content. So please focus on the language as well. That's your DNA. So this information is important. Okay, this information is important. Fine. Okay, so now move to the next part, that is structure of polynucleotide chain. So you already know it, but okay, let's quickly revise it from NCERT. So a nucleotide has 3 components. Yes ma'am, we know that. So do you know about 2 types of nitrogenous bases? Done. Uracil is present in RNA at place of thymine. Yes, we know that. So what is the another name of thymine? What is the another name of thymine? Yes everyone. What is the another name of thymine? Quick, 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 please answer it quickly. Another name of thymine, excellent Nandini, it is 5-methyl uracil. 5-methyl uracil, very good, very good. So see, nitrogenous base is linked to the OH of first carbon of pentose sugar through N-glycosidic linkage to form nucleoside, right bache? So I hope you know about it. And when a phosphate group is linked to the OH of 5' carbon of a nucleoside through phosphoester linkage, then it will be a nucleotide. So when 2 nucleotides, they are linked, so they will have 3', 5' phosphodiester linkage. So I hope now this language is clear. Okay, so sometimes what happens, Jyoti, that in class you feel like that you are understanding everything, but after the class, in the absence of teacher, when you read something from your notes or from your book, right, if you cannot recollect that, if you cannot recapitulate that, so what you people should do, you should watch the lecture again. right? You can check the recorded video. You can just increase the speed and you people can check the recorded video. Okay, and here in this chapter, this is the major problem. They said during class you feel like, okay, I'm getting everything, I'm grasping everything, because a lot of data is there in this chapter, right? So if you have done this chapter before, okay, then today's class is going to be very beneficial for you. If you're doing this chapter for the first time, again, the class is beneficial, but you have to change the way you revise. Okay, it's not mandatory that you have to be with me till the end. What I'm trying to say is, like, let's say after completing the DNA structure, you are feeling like, ma'am, okay, I got the DNA structure, but I need to revise it again. You can just pause the video. Okay, Likhita? Right, this is a genuine advice that I'm giving you people. You can just pause the video, then you can just revise everything. You can just read it from NCERT. If you are finding it difficult, you can just rewind the video, listen to that portion again, then move ahead. Right, you have to complete the lecture, but it's not mandatory that today only, and that doesn't mean you are allowed to leave the class. No, after completing DNA, divide this chapter into different parts na. Just in first part, include the structure of nucleic acid, right, the DNA experiments, the search for genetic material, the semi-conservative model, and DNA application. Divide it as a one part, then pick up the transcription, types of RNA, genetic code as another part, then the next portion as another part. So you can divide the chapter into parts, right? That's my way, that's my approach. You can divide that chapter into parts. Okay, I'll pick up the first part today, I'll pick up the second part today, I'll pick up the third part today. Right? And when you are sure ki yaar, theek hai, now I can just nail it. Okay, then check all the, right? Then revise all the parts. Then in one go you can finish this video. So that is how you have to revise. Because I got a call from the Avengers batch students, na, they were also following the Games of NEET series. They are following basically. So they were like, ma'am, I am not able to manage, right, that thing. I don't know how to revise, right? So then this is what I suggested them. And the same suggestion is for you people as well. Okay? The same suggestion. So try it. Even if you want to complete the lecture first, no ma'am, because I'm doing it for the first time, so I'll make the notes first. Then I will divide it in parts and then I'll revise. It's perfectly fine. Then also it's perfectly fine. Okay? Okay, so more nucleotides can be joined in this manner. So always remember a free phosphate moiety. Free phosphate moiety means free phosphate molecule is present at 5' end of sugar, right? That's why that end of polynucleotide chain is known as 5' end. That's what we say in DNA, na, 5' end, 3' end. So 5' end is always having, 5' end is always having free phosphate group. Thank you, Bache Ramesh Kumar, right? Then the other end of the polymer, it is having OH group, free OH of 3' carbon group. So it is the 3' end of the polynucleotide chain. Clear? And when it comes to the backbone, I already told you that is the sugar phosphate backbone, right? That is the sugar phosphate backbone. Clear, bache? Sure. So see, this is the sugar phosphate backbone. So now let's talk about the DNA structure. So tell me, what do you know about the DNA? Tell me, what do you know about the DNA? And yes, you will get the break. Let me finish the DNA structure, then you people will get the break. After break, we will start the search for the genetic material. Okay? Okay, so let's start the DNA structure. So yes, you are right that when it comes to DNA, DNA is deoxyribonucleic acid. So we know that in the DNA there will be, yes bache, deoxyribose sugar, and we know about the bases as well. But before that, what is important? Do you know the Friedrich Mischer? Do you know who's Friedrich Mischer? So bache, Friedrich Mischer in 1869, right, he was the one who discovered something in pus cell. Pus cell means in WBCs, right? Friedrich Mischer in 1869, he discovered something in pus cell. Pus cell means we are talking about the WBC. He called it as nuclein. He called it as nuclein. And later on, bache, later on, Altman recognized its acidic property. So Altman renamed it as, Okay, renamed it as nucleic acid. They renamed it as nucleic acid. Okay, so they got to know about the nucleic acid, but that quest, right, that quest for the genetic material, that which exactly is the genetic material, that quest started in 1926. Okay, that quest started in 1926. See here, see, look at this. DNA as an acidic substance present in the nucleus was first identified by Frederick Mischer in 1869. So basically it's NCERT, so it's important. He named it as nuclein, and because of the technical limitation, bache, right, because of technical limitation, they were not able to extract, they were not able to isolate such a long polymer, right? So the elucidation of structure of DNA remained elusive for a very long period, right, bache? So for a very long period they were not aware that what exactly is making the DNA, what exactly is the structure of that DNA. Clear bache? Clear bache? So you know that in 1953, right, James Watson and Francis Crick, James Watson and Francis Crick, they gave the structure of DNA. Okay, they gave the structure of DNA. They got a Nobel Prize for that as well, okay, for explaining the structure of DNA, but it was not actually their work, right? This is what I always used to say, right? It was not their work. Okay, so basically how were they able to explain the structure of DNA? They took the help from the data of, right, X-ray crystallography data, right, X-ray crystallography, X-ray crystallography. It is also known as X-ray diffraction. So bache, it was performed by Rosalind Franklin. Okay, it was performed by Rosalind Franklin and Maurice Wilkin. Okay, and Maurice Wilkin. So when it comes to explaining the structure of the DNA, so James Watson and Francis Crick, they took the help from the data of X-ray crystallography data of Rosalind Franklin and the Maurice Wilkin. And you know that Erwin Chargaff, right? He explained all that things now, at purine is equals to pyrimidine. So he took the help from these three scientists. So the data of the X-ray crystallography data of Rosalind Franklin and Maurice Wilkin helped him to explain the base pairing, the bonding. And because of Erwin Chargaff's data, they got to know that okay, purines are equals to pyrimidine, adenine is forming bond with thymine, adenine is equals to thymine, cytosine is equals to guanine. This is what Erwin Chargaff explained. Okay, so by using all that information, they explained the base pairing in DNA, they explained the DNA structure, and the DNA structure that is explained by Watson and Crick, it was the B-DNA, right? It was the B-DNA, the right-handed DNA. B-DNA, the right-handed DNA. Okay, the right-handed DNA. Clear, bache? Clear? Clear? Sabha, please check your statement again. Okay. Now I always share this story that actually James Watson and Francis Crick, right, they just without the knowledge of Rosalind Franklin, right, they used her data. Okay, whenever I explain the structure of James Watson and Francis Crick, I always used to say, right, Rosalind Franklin, by that time it was very difficult for females to pursue the career in science, right, especially at that level. Right, she went to different colleges, universities. Let's not talk about that. Right, she is also considered as the unrecognized. She's the unrecognized person. She didn't get the credit for the DNA discovery. Actually, it was her data Because of that, you know, James Watson and Francis Crick, they were able to explain the structure of DNA. She was the expert of X-ray crystallography, and she took a picture of DNA, right? That is called as photo 51. That was one of the best, right, pictures of that DNA, and on the basis of that, Watson and Crick, they were capable, they explained the structure of the DNA. Okay, so it was mainly the Rosalind Franklin's work. So she worked on the coal as well, she worked on the graphite as well, right? But as I said, so she's just like, you know, she didn't get the credit. This is what I can say. So that's my advice. You people should, okay, you people should read about it a bit. Okay, you'll get to know about the Rosalind Franklin. So she worked really hard for that. Okay, she worked really hard for that. Wait, I'll tell you one name. So she's just like you know, kind of unknown genius. Fine. So you can read about her life history. It's quite motivating. Fine. Untold story. Yeah, so basically at that time it was very difficult for females to pursue career in science. Okay, but she somehow managed, and she, you know, after many years, she joined the lab where Morris Wilkin was already working, and even he was jealous of her. Okay, that feeling na, that how a female is commanding this and that, it was the thing. And she was the expert of X-ray crystallography, and by then even na, Morris Wilkin, he was also working on DNA structure. So the head of that particular lab, he assigned Rosalind Franklin also the same work, that you should work on that. But Morris Wilkin was also jealous of her, right? In one conference also she presented her data. Okay, but that the data of X-ray crystallography, or that data of X-ray diffraction, so Morris Wilkin, without the knowledge of Rosalind Franklin, he shared that data with Watson and Crick. Okay, so by using that data, because that photo 51, as I said, like you can search photo 51, you will get that image. So that is one of the best, you know, data of that X-ray crystallography. So by using that data, they explained the structure. Later on they admitted it. So she didn't get the credit for this DNA's discovery, but she was the main person behind. Okay, she was the main person behind. Yeah, she died because of ovarian cancer. Okay, and Erwin Chargaff, you know about the Chargaff's rule, so let's discuss that, and then we will come to the then we will talk about what? We will talk about the structure of DNA. So basically, see, Erwin Chargaff, they almost explained everything. Purine is equals to pyrimidine, adenine amount is equals to thymine, and their ratio is species specific, the ratio is going to be equals to 1. So obviously what they explained, Watson and Crick, the base pairing, that's all, right? That's what they explained, right? That's what they explained, nothing else. So let's talk about the same thing. So even this is what even we are going to discuss. Yes, bache, this is what even we are going to discuss, and that is your, yes, that is your Chargaff's rule. So what do you know about the Chargaff's rule? What do you know about the Chargaff's rule? It's very important. Chargaff's rule. It's very important. Chargaff's rule. Quick. So basically, in double-stranded DNA, amount of purine is equals to the amount of pyrimidine. That's the first point. So yes, in the double-stranded DNA, you cannot apply this point to the single-stranded DNA. That in double-stranded, yes, that in double-stranded DNA, the amount of purine, okay, the amount of purine is equals to the amount of pyrimidine. Yes, that's the first point. The purine amount is equals to the amount of, yes, bache, the purine amount is equals to the amount of, it is equals to the amount of pyrimidine. The first point clear? Yes, the first point clear. So purines means your adenine plus guanine. So your adenine plus guanine is equals to your cytosine plus thymine. Am I right? Your adenine plus guanine is equals to your cytosine and thymine. Am I right? Yes bache, am I right? Clear Nandini? That's a very simple point. So if you take the ratio here, right, if you take the ratio here, so that ratio is going to be 1 and it is constant, right? It is constant species to species. Okay, I should write it properly. I should be more accurate. 1 second. That's how I'm going to write it. That will be the more appropriate. Okay, clear? Clear? Sure. So then when you talk about the base ratios, right? So it is about the purine and pyrimidine, and you know that the amount of adenine is equals to amount of thymine. Amount of cytosine is also equals to the amount of guanine. So if you take the base ratio 8 plus A plus T, C plus G, so that is going to be constant for species, means it is going to be species specific. Okay, this ratio is species specific, so please do not make the mistake here. Fine, this ratio is also the species specific. Clear bache? Clear bache? So two type of DNA is there. One is the GC type of DNA and other is the AT type of DNA, right? One is the GC type of DNA, another is AT type of DNA. Can you explain me the meaning here? Yes, what is the meaning of this line? GC type of DNA means bache, it is GC rich, means guanine and cytosine they are more, and here adenine and thymine it is more, right? Here adenine and thymine it is more, isn't it? Isn't it? So this scenario is in the case of eukaryotes. So eukaryotic DNA, okay, the eukaryotic DNA is your AT rich, and when you talk about this DNA, it is your prokaryotic DNA, it is having more GNC. So basically I simply want to say that the concentration, the amount of A plus T is more than G plus C. So obviously in that case, because adenine and thymine, they have two hydrogen bonds, right? Adenine and thymine, how many hydrogen bonds they have? They have two hydrogen bonds. So it's easy to break, right? It's easy to break the bond then. Okay, and obviously when it comes to the melting point, depends upon GC concentration. Okay, why bache? Because they both are having triple bond, triple hydrogen bond. Clear bache? Right? They both are having triple bond. Okay, that is why. Sure? Okay, so this is the Chargaff's rule, right? And you know the X-ray diffraction data. So what Morris and Wilkin explained, let's discuss that first. So see, Watson and Francis Crick, based on the X-ray diffraction data, you can also call it as X-ray crystallography. Okay, so they proposed a simple but famous double helical structure of DNA. As I said, it is the BDNA, it is the right-handed DNA, do not forget that. So one of the hallmarks of their proposition was the base pairing between the two strands of polynucleotide chain. This is what they explained, the base pairing, right? The base pairing. So, and that base pairing, this proposition was also based on our observation of Arvind Chargaff, right? So Arvind Chargaff explained the ratios between adenine and thymine and guanine and cytosine are constant. The ratios between adenine, thymine and cytosine, guanine, they are constant, right? And it is equals to the 1. So that's what you need to remember. Clear bache? That's what you need to, oh, ratios in between adenine, thymine, okay, and the guanine, cytosine, it is equals to the 1. That A over T, this is what I'm discussing. So now come to the salient features of the DNA. So they are saying it is made up of two polynucleotide chain. Yes, we are aware of it, right? And when it comes to the backbone, that is sugar phosphate backbone. So I hope you all know about it, right? So I hope you all know about it, right? That's what I told you. Sugar, nitrogenous base, phosphate. 5' end is having free phosphate. Sugar, nitrogenous base, phosphate. Sugar, nitrogenous base, phosphate. Wait. So sugar, nitrogenous base, phosphate. So you know that in between, what do we have? We have this sugar phosphate backbone, right? This side is having what? It is having sugar phosphate backbone, sugar phosphate backbone. Clear bache? And nitrogenous bases are towards the center. So wait, one more thing. This is 3' end, so here obviously it will be 5' end. See this. See, that's the point, right? That's the point. Ultimately, what is DNA? It's a double-stranded structure. That's what we know. It's a double-stranded structure. One strand is having polarity 5' to 3'. So another strand is having polarity 5' to 3', but they all are in opposite directions. They both are in opposite direction. So this is what we have. This is the 5' end, right? So synthesis is in this direction. This is the 5' end, free phosphate. So this is the 3' end, bache, free OH group. Now here, this is the 5' end. You know na, it is anti-parallel. It is anti-parallel. Anti-parallel means both are in opposite direction. Both are in opposite direction, because this is the 5' end. That's why phosphate is, right? That's why free phosphate is present. This is the 3' end. That's why free OH is present. Right? Right? So sugar phosphate, this sugar phosphate, they are making the backbone here. This sugar phosphate, they are making the backbone here. Am I right? See? Am I right? And nitrogenous bases are in center. Okay, nitrogenous bases are in center, isn't it? And you know that they are going to get connected with the hydrogen bonds. Which bond is going to connect them? Hydrogen bonds. Yes or no, students? Yes or no, students? Which bonds are going to connect them? Hydrogen bonds. So can I say that it is the hydrogen bonding which is connecting two polynucleotide chains? Yes. Can I say that, Anjani, that it is the hydrogen bonding which is connecting two polynucleotide chains? Definitely. So just look at this part. It is made up of two polynucleotide chain where the backbone is constituted by sugar phosphate and the bases project inside. I hope the language is clear. Two chains have anti-parallel polarity. The very first word is, are they parallel? Yes. Yes. Right? Two parallel lines which are never going to intersect. This is what you know. Now the word is anti-parallel. Alright, direction wise. If one is moving in this direction, another one will move in opposite direction. That's why we use the word anti-parallel. So if one chain is having the polarity 5' to 3', another one will have 3' to 5'. Understood? So bases in two strands are paired through hydrogen bonds. Adenine will form 2 hydrogen bonds with thymine. Right? Adenine will form 2 hydrogen bonds with thymine, and cytosine will form 3 hydrogen bonds with guanine. Clear, bache? Clear, bache? Clear? Clear, clear, clear. So always, so because of that, can I say that a purine always come opposite to pyrimidine? Right, Likita? Can I say that a purine always come opposite to pyrimidine? Of course. Of course. So see, cytosine, it's a 6-membered ring. Guanine, it's a 9-membered ring. Thymine, it's a 6-membered ring. Adenine, it's a 9-membered ring. So always a purine, right? Always in front of a pyrimidine or purine, you will find in front of purine, pyrimidine will be there. Right? Right? So that is important for the structure uniformity. That is important for that proper structure. See this. See this. Right? Because the purine comes opposite to pyrimidine, it generates approximately uniform distance between two strands of helix. Imagine pyrimidine, pyrimidine. Right? Imagine purine, purine. Right? The structure uniformity will not be there. So because of this, the structure uniformity is there. Right? Union distance between two strands of the helix is there. Okay, so they can ask you it as a previous, they can ask you it as MCQ, that what is the reason, right, for the uniform distance between the two strands of the helix. What is the reason for having the uniform distance between the two strands of the helix? It's very simple, students. Purine comes in front of pyrimidine. Okay, 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 okay. Right. So now, when we discuss the structure of this DNA, Firstly, let's start with the diameters. So when it comes to the diameter of the DNA, it's 2 nanometer or 20 angstroms, right? That diameter is what? 2 nanometer, 20 angstroms. Clear? Now you know that bases. So when you see the structure of DNA, right, this portion is basically, bache, the minor groove, right? I'll show you the proper structure also, minor groove, right? You know that ultimately DNA will coil over the proteins, right? So these grooves are the parts where proteins are going to interact. So this space is the major groove, right? This space is the major groove, okay, and this space is the minor groove. See, one minor groove, one major groove, one major groove, one minor groove. So they basically, this minor and major groove, right, they make the one turn of the helix, right? We basically compare the DNA structure with the spiral, right, that staircase, with the helical staircase, with the spiral staircase. So one minor and major groove, right, one minor and major groove, what are they going to do, students? These minor major grooves, they make one turn of the DNA. They make one turn of the DNA. Clear, bache? So now obviously bases are present. Like let's say adenine is present, let's say cytosine is present, let's say thymine is present there. So in DNA, right, Leharika, complementarity is there. DNA follows the rule of complementarity. Complementarity means in front of adenine, always what are we going to get? Thymine. In front of cytosine, what are we going to get? Guanine. In front of thymine, what are we going to get? Adenine. So this is the rule of complementarity. This is the rule of complementarity. And when you talk about this part, it is one base pair. What is it, bache? It is one base pair, right? Like when you consider this adenine, thymine, you are talking about one base pair. So one base pair means how many bases are there? One base pair means how many bases are there, Leharika? 2 bases, right? 2 bases. So if I'm saying 10 base pairs means how many bases? 10 base, in 10 base pairs, how many bases are there? In 10 base pairs, how many bases are there, Ramesh? 20, exactly. So now when you talk about the distance, right, see this one base and the second base, in between these 2 bases, right, what am I discussing? The structure of bDNA mainly, right, which is the right-handed one, which is the right-handed one. So when you discuss about the distance in between these 2 bases or base pair, it is 0.34 nanometer or 3.4 angstrom. Firstly, understand this. It is 0.34 nanometer, 3.4 angstrom. Now, bache, right, when you talk about the each turn of this DNA helix, right, when you talk about the each turn of DNA helix, so you see that 10 base pairs are present. 10 base pairs are present in each turn. How many base pairs are present in each turn? How many base pairs are present in each turn? 10 base pairs are present. So students, now I know the distance between 2 base pairs, right? I know the distance between 2 base pairs, that is 0.34 nanometer or 3.4 angstrom. So if I have to calculate for 10 base pairs, can I do that? Obviously I can, right? So it is going to be 3.4 nanometer or 34 angstrom, right? 3.4 nanometer, 34 angstrom. Or let's say from this part I can ask you the questions, Aaron, Leharika, Anjini, right? I can also ask you the questions from this part. Let's say I'm telling you that in between 10 base pairs, the distance is 34 angstrom. So what should be the distance in between 2 bases or 2 base pairs? You can tell me that distance. You can tell me that distance. Let's say if I change the numbers here, right? If I'm telling you that each turn is having a distance of, okay, each turn is having a distance of 10 nanometers, right? Each turn is having 10 bases, or the distance is 10 nanometer. What should be the distance in 2 base pairs? You can accordingly calculate. Okay, you can accordingly calculate. Or let's say I can ask the question in this way. The distance between 2 base pairs is, let's say 3, let's say that is a 6 point, or okay, any random number, right? Let's say I'm saying that the distance between two base pairs is 5.4 nanometer. Okay, sorry, 5.4 angstroms. 5.4 angstroms, that's what I'm saying. Listen to my question, Sabha. I am saying the distance between two base pair is 5.4 angstroms. You have to focus on the units as well. And I am saying that each turn of the helix is having 20 base pairs. Focus on the language. If I'm saying 10 base pairs means 20 bases. If I'm saying 20 base pairs means 40 bases. So what should be the distance, right? What should be the yes bache, so what should be the distance of that one turn? Like this. This is how I can ask you. Okay, so this is something basic that you need to know. So now which I am saying the diameter is 2 nanometer or 20 angstroms. Diameter means this part, right? So can I say that diameter is equals to the distance between two phosphates? Can I not say that? Like, look at this structure. Yes, look at this structure. See, in the case of this DNA, if I have to tell you the diameter, right, that's how I'm going to take the diameter. It is helical as well. That's how I'm going to take the diameter. That's how I'm going to take the diameter. So in that case, obviously if I have to consider the diameter, can I say the diameter means the distance between two phosphates? Of course. So I just changed the language, right? I just changed the language. So the two chains are coiled in a right-handed fashion, right? The two chains, how are they coiled, Ramesh Bache? How are they coiled? They are coiled in a right-handed fashion. So the pitch of helix is 3.4 nanometer, right? And they even told you that 1 nanometer is equals to 10 raised to power minus 9 meters. So you should know that, so that you can convert one unit into the another one. Fine. So they are saying the pitch of the helix is 3.4 nanometer, and there are roughly 10 base pairs in each turn. So pitch of the helix means they are talking about that one turn. So one minor and major groove forms one turn. Okay. So this is as per NCERT. So consequently, the distance between a base pair is approximately 3.4 nanometer, right? So plane of one base pair, the plane of one base pair stacks over the another in the double helix. This is going to provide it the additional stability in addition to the hydrogen bond, right? So the plane of one base pair, it stacks over the another base pair, it is providing additional stability. Hydrogen bond is providing the stability, but this is providing additional stability. So I hope the structure of the DNA is clear. So just have a look, the sugar phosphate backbone, the bases which are present there, because purine is facing the pyrimidine, so there is a uniform distance in between this DNA, right? And whenever we check the diameter, we consider the diameter between these two phosphates. That's how we used to measure it. So this is one turn, bache. This complete is one turn. Can you see that? So one minor groove and major groove, they are making one turn. This is one turn having 10 base pairs. Okay, having 10 base pairs. So the structure of the DNA clear. See this, the structure of the DNA clear, right? See, the sugar for the bases, the sugar phosphate backbone here, the same way bonding is present, right? The same way bonding is present. Okay, so minor groove, major groove, everything is clear. Sure. So see the bonding also. Look at this bonding part also. Wait. Okay, so look at this bonding part also. Clear, bache? So two hydrogen bonds are there, adenine, thymine. So this amino group of adenine is involved in bonding, and here this O, this double bond O. Okay, and here also that NH here also. So two hydrogen bonds, and here you are having 3 hydrogen bonds. Fine. Any doubt? Sure, bache? Sure. So nucleoside, nucleotide, everything is clear. So now you tell me, in the DNA, what are you going to get? Are you going to get AMP, DAMP, or are you going to find out DATP? What will you see in the structure of DNA? In that final structure of DNA, what will you see? Is it DAMP or is it DATP? Is it DAMP or is it DATP? DAMP means deoxyriboadenosine monophosphate, deoxyriboadenosine triphosphate. What should be there? What should be there? Okay, so obviously it's DAMP, so never ever make this mistake. Okay, so nucleotide is your DAMP. So if, see here, two additional phosphates are attached, you know that they are high energy bonds, right? They are high energy bonds. So when total 3 phosphates are there, then it is a nucleoside triphosphate, right? 2 phosphates, nucleoside diphosphate, but this nucleoside monophosphate, right? It is what? That is going to be there in the DNA chain, right? Right. So this bonding clear, the sugar phosphate backbone clear, sugar phosphate. So I'll share the notes in the Telegram group, right? I'll share this PDF in the Telegram group. So later on you can check all that images and you can further understand the bonding part. Okay, you can further understand the bonding part. Okay, so now we have to start the packaging of DNA double helix. So do you need break or can we continue? Do you need break? Okay, chalo break. ठीक है, so break till 8 PM. Fine. Okay. No, take the break for half an hour, because after that break, take the break for half an hour, and then after that break, the packaging of DNA double helix, the experiments, the search for the genetic material and the replication. This is what we will finish, and then we will move to the next part, transcription. Okay, so see you all at 8. No, that's your dinner break. That's your dinner break. Hi everyone. Hi everyone, welcome back. Hello. So are you people done with your dinner? Yes, Priya, Niharika, Harshu. Hi Dina, long time. Okay, so now bache, we are going to talk about the packaging of double helical DNA, right, in a nucleus, and then the search for genetic material, okay, the experiments, and finally that Michelson and Stahl experiment and the DNA replication. And then after that you people will get your next break. Okay, okay. So yes, so what we have completed so far, we talked about the structure of the nucleic acid, the bonding part. Okay, so that portion is also going to help you in the chapter biomolecule. So please revise that properly. Okay, right, revise that properly. Okay, so now come back to this topic. So we are following the NCERT, and for this particular chapter there is no need to go beyond NCERT, but yes, you have to attend the lectures of your teachers. If you know the mechanism, firstly understand the mechanism, and for understanding that mechanism, yes, you have to go little beyond NCERT. Okay, and then the topic will be easy for you. Fine bache? Fine, and then that topic will be easy for you. So after that, just revise everything from the NCERT only. There is no need to go beyond NCERT. Okay, okay, so let's start the class, students. So the proposition of a double helical structure for DNA and its simplicity in explaining the genetic implication, it became revolutionary. Okay, what is it? Done bache? So proposition of a double helical structure for DNA and its simplicity in explaining the genetic implication became revolutionary. Very soon Francis Crick proposed the central dogma in molecular biology. Another important MCQ, right bache? It is another important MCQ. Who gave the central dogma, right? Who gave the central dogma in molecular biology, or central dogma of information? The answer is Francis Crick, not James Watson, just Francis Crick. So another important PYQ, and here the another important PYQ. So basically, what is the central dogma of information? It is the flow of information. One thing that we all know is that genetic information is stored in DNA, right? And I'll tell you the reasons that why do we consider DNA as the genetic material. Now this is what we are going to discuss. So the information is there in the DNA, right bache? So when you talk about the flow of information, the central dogma of information, so DNA is not directly going to make the protein. No, first of all, DNA will make a primary transcript of it, right? A kind of replica of information that DNA is having, right? Right, so that is known as transcription. What is it? Transcription. And then that mRNA will form the protein. That is the translation. And when it comes to the DNA, DNA replicates. So this is the flow of information. Clear bache? Clear bache sign? This is the flow of information. So what is the flow of information? DNA to mRNA to protein, right? So this is the flow of information, and the topic which is given under the protein, which is given there in your syllabus, protein biosynthesis, first point. Now there is the reverse flow of information as well, central dogma reverse, and in that what is happening? RNA is forming the DNA. That is the complementary DNA basically, but RNA is forming the DNA. That is the reverse flow of information, central dogma reverse. And for that bache, we use the word teminism. What is the word for that? What is the word for that, students? Temanism, the reverse flow of information. RNA is making the DNA. Clear? RNA is making the DNA. Okay? Okay? RNA is making the DNA, reverse flow of information, and for that the enzyme used is your reverse transcriptase and the process is reverse transcription. Okay, enzyme is reverse transcriptase. Another important MCQ. Clear, bache? Clear? So first of all, let's talk about the packaging of DNA double helix, and then we will talk about the next part. Okay, so basically we know that when we talk about the structure of the DNA, let's finish it very quickly. Yes, we know that it is double stranded, right? Let's talk about the humans, or let's talk about the eukaryotes. So you know that in the case of eukaryotes, bache, what type of DNA do we have? We have linear DNA, right? What type of DNA do we have? We have linear DNA, isn't it? Isn't it? We have linear DNA. Right, bache? Right, bache? So linear DNA is there, isn't it? Isn't it? And you know that even if you talk about the humans, in the case of humans, bache, right, our DNA is 2.2 meter long. When we talk about the DNA, you know that the number of base pairs or the number of nucleotides, they are going to decide the length of DNA. Yes, this is what I just said. The number of nucleotide is going to decide the length of the DNA, or the length of the DNA. So if I'm talking about the humans, let's say I'm taking the example of a diploid cell. So it is 6.6 into 10 raised to power 9 base pairs. Right? In the diploid cell, what do we have? 6.6 into 10 raised to power 9 base pairs. That's what we have. Now we have to calculate the length. So it's very simple. You know that in between two bases or two base pair, this is the distance, 0.34 nanometer. And if I have to convert it into the meter, so what am I going to write? What am I going to write? I will multiply it with 10 raised to power minus 9. Right? This is what I'm going to do. Yes, bache. Yes, bache, this is what I'm going to do, because I have to convert it into the meters, right? Right, in the NCERT itself it is given. It is given that when you talk about the nanometer, 1 nanometer is having 10 raised to power minus 9, right? It is equals to 10 raised to power minus 9 meters. 1 nanometer is equals to 10 raised to power minus 9 meters. So here 0.34 nanometers. So that's how you are going to, right? That's how you are going to calculate it, isn't it? Isn't it, Niharika? Yes, bache. So now what's the next step? So this is telling us about the, right, bache, this. So when you multiply it, what are you going to get? This is your result, that your human DNA is 2.2 meter long. What is it? It is 2.2 meter long. But bache, nucleus, it's just 10 raised to power minus 6 meter, right? Look at the distance of the, look at the nucleus also. It is just 10 raised to power minus 6. These are the dimensions of the nucleus, of a typical nucleus. So how are you going to fit a 2.2 meter long thing into that small thing? Obviously you have to pack it, you have to fold it, you have to fold it again and again, right? You have to fold it again and again. Okay, okay, and that's what we are going to discuss now. But before that, can you tell me the length of the E. coli's DNA? Yes, can you tell me the length of the E. coli DNA? E. coli's DNA is circular, right? The DNA of E. coli, it is circular. But can you tell me the length of the DNA of length of E. coli's DNA? Yes, anyone in the class? Anyone in the class? Bache, any idea about it? Do you have any idea about it? You need to focus on the distance first. You need to focus on the distance first. Yes, it is 1.36, right? It is 1.36 what? Millimeter, right? It is 1.36 millimeter. Okay. Okay, so now I have one question for all of you. You said it is 1.36 millimeter. Right, so now can you tell me the number of bases present in E. coli? That is another important question. Yes, number of bases present in E. coli. Do you have any idea about it? Yes, please let me know in the chat section. Number of bases present in E. coli. It is given in NCERT. It is given in NCERT. Number of bases, number of bases present in E. coli, a number of base pairs present in E. coli. Base pair is the word, right? So it is 4.6 into 10 raised to power 6 base pair, right? 4.6 into 10 raised to power 6 base pairs. That's what you have in E. coli, right? So now that's your homework. You will tell me about the distance between two base pairs. Okay, so that's what you are going to calculate. That's your homework. Fine, that's your homework. Fine, bache. Okay, so when you talk about the packaging, okay, so here you can see whatever things we have discussed so far, it is given in NCERT. So you cannot miss that part. Okay, okay. So first of all, let's talk about the prokaryotes. Now I am telling you about E. coli. What is E. coli? E. coli is a bacteria. E. coli is a prokaryote. And bache, when you talk about the prokaryotes, you know that in their case, there is no true nucleus. The genetic material is directly there in the cytoplasm, and we used to call it as nucleoid. We used to call it as naked DNA. Do you know that? That is nucleoid, naked DNA. We use the word genophore for that also. What's the term that we use for it? Genophore. And even, right, the prochromosome. Right, even the prochromosome, that's the terms that we use. Okay, so now what's the point here? The genetic material, it is directly there in the cytoplasm, but it is also coiled. Okay, it is also coiled, it is also folded. So yes, we need the proteins for that folding. Right, here also in prokaryotes, that DNA is forming the loops. Right, that DNA is forming the loops. Okay, bache. So see this, in E. coli, though they do not have a defined nucleus, the DNA is not scattered throughout the cell. Okay, okay, and DNA is negatively charged, right? DNA is negatively charged. Why? Because of phosphates. So if we want to coil that DNA, we need the proteins, and that proteins need to be positively charged. Okay, that proteins should be positively charged. And here in the case of prokaryotes, right, polyamines are going to solve our purpose. Right, polyamines are present. In the case of prokaryotes, Leharika, what do we have? We have the polyamines. Clear, bache? Clear, bache? So DNA is not directly scattered. It is going to coil. It is going to form such loops. Okay, and which protein it is? These are polyamines. These are polyamines. Is that clear? So remember, in E. coli, in prokaryotes, histones are absent. Okay, histones are absent. They are devoid of histones. Fine, histones are absent. They are devoid of histones. But instead of that, positively charged polyamines are present in their case. Now come to the eukaryotes. Right, this is about the prokaryotes because simple organization is there. Now come to the eukaryotes. This image is explaining everything. Okay, this image is explaining everything. Okay, okay, okay. Right, so in the case of eukaryotes, we know that, let's take the example of humans only, 2.2 meter long DNA. So we know that we have the nucleus where we have to fit it. Okay, so now if you just look at this, so this DNA, double stranded DNA, okay, it will coil, bache. And how will it coil? With the help of histone proteins. It will coil, it will coil, it will coil. It is going to form something like that. See, initially the DNA was like this. The DNA was like this. This is my helically coiled DNA. Right, now this helically coiled DNA will wrap around the histone proteins. Right, it is going to wrap around, it is going to coil around the histone proteins. Can you see that? Can you see that? And then it will form a structure like this. It is going to form a structure like this. And after that, what is going to happen, bache? What is going to happen? Further coiling will occur. Right, see, now these things are going to coil further. These things are going to coil further. Right, a kind of solenoid will form, and that will further coil, will form solid loops, loops. Finally, you will get this, your chromosomes, the structure like this, the condensation like this. Right, the condensation like this. That's what we have to study. So DNA, further coiling. See, now these histone proteins, these structures are further coiling, they are piling, they will pile up and then they will form a solenoid like structure. Further, see, the loops will form, further loops will form, and that loops will again become compact, and then they will form the chromosome. Then they will form the chromosome. That's how it is going to work. So when you talk about the eukaryotic packaging, the very first thing that you should know is there are 3 levels of packaging here. How many levels of packaging are there? 3 levels. Right, in eukaryotes I'm discussing. The very first level is nucleosome model. Second is solenoid model. Okay, don't get scared with these fancy names, it's very easy. Third is radial loop model. These are the 3 levels. Okay, how many levels of packaging are there? There are 3 levels of packaging, where what is happening, students, right? Your DNA will be coiled, right, bache? The very first level is what? It is the nucleosome, then solenoid, then comes the radial loop model, right, bache? That is how it is going to pack. So very first thing that we need to know is histone proteins. Right, in the case of eukaryotes, histone proteins are going to help in that packaging. Now bache, these histone proteins are obviously, these are basic proteins, right? What are they? They are basic proteins, means they are positively charged, right? If something is basic, of course it is positively charged. What is it? It is positively charged. And DNA being negatively charged, yes, we need the positively charged, right? Yes, we do need the positively charged proteins for its coiling. Okay, and what are they? They are the histone proteins. And why these proteins are positively charged, bache? Because of the basic amino acids. You know that amino acids are going to make the protein. Okay, so we have basic amino acids. So basic amino acids present in histones are lysine and arginine. What is it? It is lysine and arginine. Right, bache? Right? This is just for your information. This is just for your information. If you talk about the basic amino acids, okay, the trick is HAL, H-A-L. What is the trick? HAL, H-A-L. So H stands for histidine, okay, A stands for arginine, fine, and L stands for lysine. But when you talk about the basic amino acids here in histones, they are lysine and arginine. What is it? Lysine and arginine. So it's a PYQ of 2020, and it is a repeated question. Right, it is a repeated question. Clear, bache? Okay, so now when you talk about the histone proteins, you have 5 histone proteins: H1, H2A, H2B, H3, H4. Right, H1, H2A, H3, H4. This is what we have: H1, H2A, H3, H4. So everyone write down H1, H2A, H3, H4 in the chart section. Quick. Write down H1, H2A, H3, H4 in the chart section. Quick. Write down the name of histone proteins. Right, write down the name of histone proteins in the chart section, and please be quick. So we have 5 types of histone proteins. Okay, 5 types of histone proteins. Okay, so out of that, H2A, H2B, H3, H4, they are going to make the nucleosome. Right, and this one, H1, is going to be the linker histone protein. Right, it is going to be the linker histone protein. Please remember. Okay, see, H2A, H2B, H3 and H4, they are going to form 4, right? Basically 2H2A, 2H2B, 2H3, 2H4, like 2 copies. Okay, bache, 2 copies of these. Okay, 2 copies of these amino acid, it is going to form the of these histone proteins. It is going to make the octamer. Okay, it will make the octamer. This is the octamer. Octa means 8, something which is made up of 8 subunits. Okay, so here 2 copies of H2A, 2 copies of H2B, 2 copies of H3, 2 copies of H4 are there. Okay, okay. So 2 copies of these amino acid, it is making the octamer. Right, it is making the octamer. Now what is going to happen? Your negatively charged DNA is going to coil over this octamer, and when it will coil over this octamer, then bache, you will use the word nucleosome for it. Right, you will use the word nucleosome for it. So please do not confuse the words nucleoid, nucleolus, nucleosome. Nucleoid, the undefined nucleus of prokaryotes, it is nucleoid. Nucleolus, which is present in the nucleus, right, which is not covered with the membrane, that aggregated part in that nucleus, not covered by any membrane or something, it is nucleosome. Right, when DNA will wrap around this histone octamer, this is the nucleosome. Right, so near about 200 base pairs of DNA are present over this nucleosome. Okay, so it's not like that there will be only one nucleosome. No, there will be many. Okay, there will be many, isn't it? Many. These cute octamers, they will form. Yes or no, bache? These cute octamers, they will form. So DNA is going to coil over it. DNA is going to coil over it. It's very simple, isn't it? It's very simple, right, bache? So near about 200 base pairs, the word is base pairs, they are present over here. Okay, now ma'am, what is the role of that linker histone protein? Can you see, bache, this is one nucleosome, this is another, and in this way you have so many nucleosomes. Varun bache, 1, 2, 3, you have so many nucleosomes, right? Don't you think here, right, now this structure that we have, we use the word chromatin for it, a kind of basic, you know, that basic unit, right, like chromosomes. When you talk about the chromosomes, chromosome is having DNA and protein. What is that? That is basically the chromatin. Chroma means color, it will get stained. Okay, that is the chromatin. When your DNA is coiled over the histone proteins, it is your chromatin. This is your chromatin. And when you see that this is one nucleosome, this is another, so here in between, that this free DNA which is present, it is known as linker DNA, or you also call it as spacer DNA. Right, it is the linker DNA or the spacer DNA, and your H1 is attached to this linker DNA. Your H1 histone protein is attached to this linker DNA. Are you getting it? So you should know these things, they are important, right? They are important. So even when you see the diagram from NCERT, this is the diagram. So see, this is nucleosome, histone octamer actually it is. So it is the core of histone molecule over which the DNA will coil. So DNA will coil like this, and this one is the H1 histone protein, which is linked to the linker DNA, Right? Clear? So don't you think that here these nucleosomes are just looking like the weeds on a string, right? These nucleosomes, they are looking like the beads on a string, like this. It is something like this. So this part present here is the spacer DNA, linker DNA. Of course, it is transcriptionally active. It will give us the information for the formation of mRNA. Yes, actually it is looking like a wow. Now the point is, now see, different levels of packaging. This wire, you are coiling it like this, fine. Now further, you are coiling it like this, right? Further you are coiling it, right? Same as the case here. So this is the first level of packaging, right? First model of packaging. Then comes the solenoid model. So don't you think that because of this packaging, don't you think that there will be the change in the dimensions as well? Yes, students, don't you think that there will be the change? Yes, there will be the change in the dimensions as well. Like if I talk about the DNA is 20 angstrom. If you talk about this nucleosome, it is near about 100 angstrom. Only this nucleosome. DNA is having a diameter of 20 angstrom, but when you talk about this nucleosome, it is having a diameter of 100 angstrom, right? 100 angstrom, or you can simply say 11 nanometer. In terms of nanometer, it will be 11 nanometer. I'm saying that roughly it is 100 angstrom. Okay, so obviously look at the diameter also. Right, look at the diameter also. So now when you talk about the solenoid model, it is the second level of packaging. Your nucleosome fiber will further coil into a solenoid fiber. Right? So basically it is the second level of packaging. Okay, so now these nucleosomes, they will further coil and they are going to form the solenoid, right? Just like the solenoid. Clear, bache? Is that clear? So again it is the further coiling, right? Again it is the further coiling. Is that clear? Is that clear, bache? So here in the solenoid fiber, the solenoid fiber is having 6 nucleosomes per turn. Okay, it is having 6 nucleosomes per turn. Is that clear? Okay, is that clear? Okay, so here obviously the diameter will again change. That will be 30 nanometer. So we started the story from 2 nanometer, then 11, then 30. And now see the third level or the last level of packaging, right? As I said, it is the radial loop model, right? That further this solenoid will also pack, right? The solenoid will also pack, right, bache? Yes or no? The solenoid will further pack and it is going to form the loops. Can you see that? It will form such loops. So this is, and these loops are having a diameter of 300 nanometer. So 2 nanometer, 11 nanometer, right? Further you are having 30 nanometer and then 300 nanometer. Clear, bache? 300 nanometer. And obviously for the third level, okay, bache, for the third level of packaging, you need, right, basically what do you need? You need other proteins also, right? What do we need? We need other proteins also, and that are the non-histone chromosomal proteins. Okay, non-histone chromosomal proteins. So in NCERT it is given, right? In the NCERT it is given, na? It is given, na? They mentioned this word, na? NHC. What is that NHC? Non-histone chromosomal protein. So they will further help in this packaging. So DNA, then nucleosome, then solenoid, then radial loops. For radial loops, we need non-histone chromosomal proteins. They will further help in the folding. Further folding will be there, right? But these fibers will further compress and they are going to form this. See, they are going to form such fibers and finally you will get your chromosome, right? Finally you will get your chromosome. Clear, bache? Wait, I'll show you one more image. See this. So nucleosome, right? In some books, bache, it is given as 10 nanometer. In some books it is given as 11 nanometer. So 10 to 11 you can consider. Okay, then see, look at this solenoid fiber, 30 nanometer, right? And then look at this radial loop. Further coiling is there. Clear, bache? Further coiling is there, and finally the chromosome, that condensed chromosome. So when you are taking this part of chromosome, only one, right, like this in monad form, it is 700 nanometer, and when it is like this, so this is 1400 nanometer, right? 1400 nanometer. Is that clear? Are you sure? Okay, so 2, then 11, or you can even consider 10, 30, 300 nanometer, 700. Okay, and when this is the metaphase chromosome, 1400 nanometer after duplication, it will be like this. So that is basically the, right, bache, that is basically the packaging of DNA double helix. Is that clear? So see, the NCERT, there is a set of positively charged basic proteins known as histones. We know that, right? Known as histones. Wait. Done. Packaging clear. So question can come from the amino acids, right? 5 types of histone proteins, and they can ask you when the non-histone chromosomal proteins are going to be used. Okay, so this is what you need to remember. Fine, bache? Okay, so protein acquires charge. It's not working. Wait. Let me refresh it. Okay, so it is going to take some time. Okay, so even our screen is demanding rest. From so long you people are taking long marathons, hai na? We need some rest. It's okay, chalo, we will revise verbally. So basically what is going to happen, the question will come from the histone proteins. Why histone proteins are bache positively charged? Because of the positively charged amino acid. What are that positively charged amino acids? That are your lysine and arginine, right? That are your lysine and, okay, I don't know what is happening, lysine and arginine. Clear, bache? So both the amino acid residues, they carry positive charge in their side chains. Do you remember the structure? Do you remember the structure? Right? If it is a basic amino acid, it will have one extra NH2. Okay, if it is an acidic amino acid, it will have one extra COH. Okay, it is going to have one extra COH. Okay, so histones, they will be organized in the form of the octamer. So when are you going to call it as nucleosome? Very important thing. When DNA coils over this histone octamer, then it is a nucleosome. Okay, then it is a nucleosome. Clear? So under electron microscope, you know, it looks like the beads on the string. Okay, nucleosome. These are chromatosomes, further coiling. These are active genes. Why? Because of the space. We will talk about it. This is that solenoid that I was talking about. And further loops will be there. Further the condensation will occur. Okay, any doubt? Yes? Any doubt? So, okay. The packaging, okay. So now they are saying the chromatin, that is more densely packed. Now bache, we need to focus on two words. One is euchromatin and another is heterochromatin. Euchromatin and heterochromatin. Now you have seen that packaging, Niharika. You all have seen that packaging. And if you people have noticed that sometimes in between you see the spacer DNA, right? The DNA which is not very densely packed. Right, some free DNA is there, and sometimes you see that DNA is so tightly packed that we cannot see that, right? It is so compactly packed. Okay, ultimately when you talk about the central dogma of information, you know that the DNA will form mRNA, right? You know that the DNA is going to form mRNA, and that mRNA is going to form protein, isn't it? DNA is going to form mRNA, and that mRNA is going to form the protein. That's what we know, right? That's what we know. So if I have to make mRNA from the DNA, right? If I want to make mRNA from the DNA, obviously that DNA needs to be available, na? Right? It should be transcriptionally active, na? Isn't it? It should be transcriptionally active, na? Right? It should be transcriptionally active, na? Yes or no? Yes or no? So when that DNA is transcriptionally active, when it is available for transcription, then it will be euchromatin. It will be euchromatin. And which DNA is transcriptionally active? Which is loosely packed, which is having a space in between. And that space, because it is not so tightly packed, so in between, like your linker DNA, like your spacer DNA, we can transcribe it, right? We can make mRNA from it. Okay, so transcriptionally active DNA is loosely packed, that euchromatin. Okay, it is genetically active because all the genes, they are giving us the information. Clear, bache? And if I talk about the stain, it is lightly stained, right? It is lightly stained. See, stained lighter. And this euchromatin, bache, it is present. Okay, it is actively present in prokaryotic and eukaryotic genome. The euchromatin, it is present in both. the prokaryotes as well as eukaryotes. Okay, they are not sticky, they are present at inner side of nucleus, allow gene to form the protein, right? But now when DNA is very tightly packed, it's very tightly packed, it is not available for transcription, because if I want to make mRNA from the DNA, I have to open the DNA, right? I have to copy the information, then I can make the mRNA. It's not like the DNA is like this and one enzyme will come and make the mRNA. No, it has to open the DNA, and then as per that rule of complementarity, it has to add the bases, and accordingly the RNA will form, students. Okay, accordingly the RNA will form. Is that clear? Is that clear? So that is why when the DNA is very compactly packed, it is not available for the transcription. So it is transcriptionally inactive, it is highly packed, and yes, it is darkly stained. These 3 points are the one which are given in NCERT. And few extra points for your knowledge, that heterochromatin is only present in eukaryotic genome. They are not present in prokaryotes. Euchromatin, it is present in both prokaryotes as well as eukaryotes, but heterochromatin is only present in prokaryotes. Then genetically inactive, it is obviously present at the periphery of the nucleus. Okay, and that's it, that's all. And if you know, right, although we have to discuss the human genome project, from human genome project we know this thing, that only less than 2%, remember, less than 2% of DNA. Do you remember that part? Less than 2% of DNA is going to make the protein. Less than 2% of DNA is going to give us the information. It is going to make the protein. Okay, it is the one which is transcriptionally active, and rest is what? Transcriptionally inactive. So we are talking about the heterochromatin there. Hope you can relate. So this part is important. Okay, this part is important. So any doubt? Yes, bache, any doubt? Okay, so now let's talk about the experiments, the search for the genetic material. So if there is any doubt, do let me know. If there is any doubt, do let me know. And after completing it now, we will talk about the properties of the genetic material. So let's go as per your NCERT. Fine, as per your NCERT. So as I said that in 1869, I'm repeating this part again, okay students, that in 1869 Frederick Mischer, right, in the pus cell he obtained this nuclein, but at that time, because technically we were not that superior, so it was very difficult to extract such a long polymer and to study. And moreover, no one paid attention that which one is actually at molecular level, which one is something which is actually passing from one generation to another, right? So as I said, by 1926, the quest to determine that which one is the genetic material, right, at the molecular level, which one is the genetic material, it started in 1926. Okay, so when you talk about the experiments, the search for the genetic material, we mainly discuss two experiments. One is the transforming principle, another is the transduction. One is the transforming principle, another is the transduction experiment or the blendings experiment. Now when it is the transforming principle, so this experiment was performed by, this is the first experiment, and the second main experiment that we have to discuss is Hershey and Chase experiment. So transforming principle, what's the word bache? It is the transforming principle. So this experiment was performed by Griffith. Who performed this experiment bache? Griffith. It is actually the Griffith's experiment. So in these experiments now we are going to discuss the things point to point. Okay, point to point we will discuss the things. So who performed this experiment? Your Griffith, Frederick Griffith. Or and when yes, when is also important, 1928, right? So that's Frederick Griffith, he performed the experiment in 1928. So what he did, he took bache a bacteria. Which bacteria? Streptococcus. Which bacteria? It's Streptococcus, also known as pneumococcus, right? This is also known as pneumococcus, also known as diplococcus. Okay, so can you tell me the meaning of coccus here? What is the meaning of coccus here? Yes, bache, what is the meaning of coccus here? Coccus means spherical, right? What is the meaning of coccus here? Coccus means spherical. So it was a spherical shaped bacteria. Clear, bache? Right? And streptococcus bacteria, it used to cause what? It used to cause the pneumonia. Now, it is streptococcus, right? Which bacteria it is? It is streptococcus. So, bache, he took 2 strains of this particular bacteria. One is S3 strain, okay, and another is your R strain, R2 strain or the rough strain. He picked up 2 different strains. Now, see, in bacteria, in prokaryotes, you know that diversity is too much, isn't it? In prokaryotes and bacteria, you know that diversity is too much, right? We are not that sufficient that, you know, we can study the different bacteria or prokaryotes. I always used to mention, even in biodiversity, you talk about the number of species, right? Do you remember that? Do you remember that number of species that we discuss in the biodiversity? More than 1.5 million species, right? Somewhere around 1.7 to 1.8 million species are present on earth. We still don't calculate the prokaryotes there, because in prokaryotes variations are there, right? At molecular level, different bacteria, they are different from each other. Now when I'm saying streptococcus, when I'm saying pneumococcus, when I'm saying diplococcus, right, in these bacteria, they are strains, they are different strains. Basically that is streptococcus only, but there are structural, you know, structurally they are not ditto same, right? Structurally they are not ditto same, right? There are different things as well. Like, firstly we started with the S3 strain. S stands for smooth, R stands for rough here, right? But when we study the structure of bacteria, do you remember one thing, right? That firstly plasma membrane is there, that plasma membrane is covered with cell wall, and that cell wall is further covered with the cell coat. Do you remember? Outermost covering is cell coat, which is also known as glycocalyx, right? Which is also known as glycocalyx. Then there is the cell wall, right? Then there is the cell membrane, isn't it? Then there is the cell membrane. So, bache, in the case of S3 strain, in this particular bacteria is having the outer capsule, right? This particular bacteria is having the outer capsule, right? Outer coat is there, like cell coat. You know, it's having 2 forms, the capsule and the slime layer. The capsule and the slime layer. So this smooth strain bacteria is what? It is capsulated, okay? It is capsulated, it is having the capsule, right? And that capsule is obviously having polysaccharides and other things. Mainly polysaccharides are there. Now when you talk about the R strain, it is non-capsulated. It doesn't have that capsule, okay? It doesn't have that capsule. Now what's the point here? Now when you talk about the S3 strain, why are you calling it as smooth strain? Because when we see its culture, so smooth colonies are available, right? Smooth colonies are available, okay? And here when you talk about it, so what do you have here? The rough colonies. And moreover, due to the presence of this capsule, this capsule is actually pathogenic. This S3 strain, right, but this S3 strain is what? This S3 strain is the pathogenic one, okay? Pathogenic one. It is the virulent one. It is the pathogenic one or the virulent one. What is the meaning of being virulent? Means it causes pneumonia, right? This bacteria, it causes pneumonia. And which strain of bacteria causes pneumonia? That's your S3 strain, right? That's your S3 strain. Clear, bache? It is the virulent one, it is the pathogenic one, okay? Now when you talk about the rough strain, which is non-capsulated, it is not having that capsule, that's why it is non-pathogenic, that's why it is non-virulent. Understood? That's why it is non-pathogenic, and that's why it is non-virulent, right? It is non-virulent. So he took these 2 strains for the experiment. Now look at the experiment, right? So firstly, he took the S strain of bacteria, he injected into the mice died, of course, because of pneumonia. Isn't it Yashaswini? Yes, in the very first step, what happened? They took the S strain of bacteria, right? That S strain was injected into the mice, right? And the mice died. Now he took the R strain, because it is the rough one, it is the non-virulent one, it is the non-pathogenic one, it is not going to cause pneumonia, so mice lived, right? Now after that, Griffith was able to kill bacteria by heating them, right? Griffith was able to kill bacteria by heating them. So he observed that heat killed S strain, like he took the S strain bacteria, he heated them, right? So that's why we are using the word heat killed S strain. Heat killed S strain, because that heat is going to destroy the outer capsule. Is that clear? That heat is going to destroy the outer capsule, right? So Griffith was able to kill bacteria by heating them. So he observed that heat killed S strain bacteria when it was injected into the mice. It did not kill that mice. Why? Because of that heat, the capsule, that capsule will get destroyed, right, Niharika? Right, Niharika? Yes or no? Yes or no? Right, that capsule will get destroyed. So when there is no capsule, means no pathogenicity, right? And because of that, mice is going to live. And then he took the mixture of S strain, which is heat killed, plus live R strain, right, Ramesh? What he did, he took the S strain, which is heat killed, and live R strain, and when he injected it into the mice again died. So it's a question mark. It's a question mark, because Shakti, individually this S strain heat killed bacteria, right? Individually this S strain heat killed bacteria, it is non-pathogenic. Even that R strain is also non-pathogenic. Then what happened? Right, when we injected both into the mice, why mice died? So it was like a question mark. It was like a question mark for Griffith. And what Griffith concluded, that there was something in this S strain, right? There was something in that S strain that converted this R strain into the virulent one, right? There was something in that S strain, right? Because of that, R strain picked up that. R strain started forming the capsule, and R strain became virulent one. Clear? So he was not the one who directly mentioned it is the DNA. No. Right? He concluded that R strain bacteria had somehow been transformed by the heat killed S strain. Right? So he gave the transforming principle, that R strain was transformed somehow by the S strain. Right? So some transforming principle, right? Some transforming principle got transformed from heat killed S strain into R strain, and R strain started synthesizing the smooth polysaccharide coat and become virulent one. Clear, bache? So something has transferred. The genetic material has transferred from S to R strain. Okay, but he didn't mention, I'm repeating this again, he didn't mention the biochemical nature. Understood? He didn't mention the biochemical nature of that particular macromolecule. Okay, particular macromolecule. Understood? And in general also, bache, we discussed three things now: conjugation in bacteria, transduction and transformation in bacteria. These are the three things that we discuss in bacteria. I hope you know that. I hope you remember. Conjugation, transduction, transformation. Conjugation, transduction, transformation. Do you remember that? Conjugation, transduction, transformation. So actually, what is that transformation? Right? In general, what is that transformation? When bacteria pick up the genetic material from surrounding, and right, what is transformation, students? That bacteria pick up the genetic material from surrounding and incorporate that genetic material into its own DNA. Clear? In general, what is transformation? As of now, Griffith was not aware of it, but I am telling you people that what is this transformation. Hope you know about this transformation, Nandini. That what is transformation? That the bacteria is going to pick up the genetic material from the surrounding and it is going to incorporate that genetic material into its DNA. Understood? Understood? So now when it comes to the biochemical characterization of the transforming principle, you know, many scientists, they try, right? And people used to believe that it is the protein which is the genetic material. Okay, people used to believe that it is the protein which is the genetic material, but Oswald Avery Colin MacLeod, McLean McCarthy, they conducted one experiment, right? And they explained that it is the DNA which is the genetic material, right? So in the exam, in the final NEET exam, they ask you the question, right, that who did the biochemical characterization of transforming principle? So MacLeod, McCarthy and your Avery, okay? MacLeod, McCarthy and the Avery. Bache, Shrinam, we will discuss it now, okay? Right, from 1993 to 44. So they worked to determine the biochemical nature of the transforming principle of the Griffiths experiment. So they extracted, isolated everything from heat-killed S strain. Why they picked up heat-killed S strain? Because heat-killed S strain transformed the R strain into the virulent one. So they exactly want to check that what compound it is, what macromolecule it is which is actually doing it. So from the heat-killed S strain bacteria, they isolated everything. They isolated all the biochemicals, right? They purified biochemicals, the proteins, the DNAs, the RNAs, right? From the heat-killed S cell to see which one could transform live cell into the S cell, right? Live cell into the S cell. Clear, bache? Clear, bache? So they discovered that it is the DNA which is going to transform the R cell into the S cell. But how? See, various experiments, they conducted various experiments. Let's say, I'll give you one example. Let's say they took this test tube. Here you have live R strain, okay? Let's say here they added the protein, okay, and they added various enzymes like, let's say here they added, I'm just giving you one example, DNAs. Do you know what is DNAs? Do you know what is DNAs? In some books it is written like this, or it is also written like this, DNAs. Yes, anyone in the class, what is DNAs? Anyone in the class, what is DNAs? Bache, yes, it is a nuclease. What is the meaning of nuclease? Nucleic acid digesting enzyme. So if it is a DNase, it's a DNA digesting enzyme. It is the DNA digesting enzyme. Understood? Right? So now let's say they took the test tube, they added the live strain bacteria, they added the protein from heat-killed S strain. They added the protein from heat-killed S strain bacteria. Clear, bache? Now, let's say if I'll add DNAs here, or I'll add, okay, not DNAs. Okay, in general, I'm asking you, if let's say they added the protein, so what do you think? The transformation will occur or not? Yes? What do you think? The transformation will occur or not? In general, I'm asking you. In general, I am asking you, the transformation will occur or not? They took the protein from heat-killed S strain, they added that protein into the R strain. Students, how can you say that transformation will occur? It's a big cross. Thank God. Shanmugam, thank God. Very good, Anjani. Excellent, Harshi. Obviously, no transformation will be there because it is a protein. It is a protein. Clear? What is it? It is a protein. So protein is not going to transform. That's why I asked it individually. Okay. What are you doing, Nandini? Do you think that protein is going to transform? Protein from heat-killed S strain is going to transform R strain. And let me tell you, if a bacteria will be heat-killed, the proteins, they will denature. Right? No transformation will occur, obviously. And that silly mistake will result in the deduction of 5 marks. Right? Literally, that silly mistake, it will result in the deduction of 5 marks. Right? Very bad. So no transformation will occur, of course. Be attentive, please be attentive. Chalo. Now another example. Let's say here you have the test tube. They added all the content of heat killed. Right? I'm asking you this question. Please try to answer. They added all the biochemicals from heat killed S strain. Right? They added all the biochemicals from heat killed S strain, and here you are having R strain, live R strain. Now, along with that content, they added RNAs. So what do you think? Transformation will occur or not? What do you think? Transformation will occur or not? Yes, transformation will occur or not? Just a question. Just a question. Those who are saying yes, you really need to revise this topic. Guys, I'm again telling you, again I'm asking my question. Here you have live R string. You have added all the biochemicals from heat killed S string. And I said that you added RNAs here. What you added? You added RNAs here. So some students are saying that no transformation will occur. How can you say that no transformation? Students, definitely here the transformation will occur. Why? Why? Because this RNAs will destroy RNA only, right? This RNAs is going to eat RNA only. And you know that it is not the RNA which is responsible for transformation, right? If instead of RNAs, I'll add protease here, proteoses here, then what do you think? What do you think? If proteases are added, then what do you think what is going to happen? Transformation will occur or not? Transformation will occur or not? Definitely it will occur. What if I'll add DNAs? What if I'll add DNAs? What if I'll add DNAs? In that case, what is going to happen? In that case, what is going to happen? Transformation will be there or not? Of course, no transformation, because it is going to digest DNA, na? So obviously there will be no, in that case there will be no transformation. Fine. So please understand the process first. Okay, please do not cram it. Understand it. MacLeod, Avery, Carty, right? They did the biochemical characterization of the transforming principle. They were the one who said it is the DNA which is the genetic material, not the protein. Right? Before that, people used to think it's the protein which is the genetic material, which is not a fact. Because when they treated these biochemicals from heat killed S strain, when they treated it with DNAs, transformation didn't occur. Why no transformation was there, students? Why no transformation was there? It's simple, because DNA will be digested. Okay, the DNA will be digested. Okay. So please do not cram, understand that. So they also discovered that protein digesting enzyme, RNA digesting enzymes, they did not affect transformation, but it was affected by the DNAs. So I hope now it's clear, right? But still, by then also many scientists, many co-scientists, they didn't believe that it is the DNA which is the genetic material, right? They didn't believe that. But that unequivocal proof, that final proof that actually it is the DNA which is the genetic material, it was given by Alfred Hershey and Martha Chase in 1952. Okay, and that is your transduction experiment, or it is also known as your blending experiment. Fine, it is your transduction experiment. It is also known as blending experiment. And bache, this experiment, it will be done in 3 steps. Okay, infection, blending, centrifugation. Infection, blending, centrifugation. These are the 3 steps of this experiment. Clear? These are the 3 steps of this experiment. Clear? Infection, blending and centrifugation. Transduction experiment it is. So here he used Escherichia coli and your T2 bacteriophage. Okay, E. coli and T2 bacteriophage. So bache, what is a bacteriophage? Bacteriophage is a virus. What is a bacteriophage? Bacteriophage is a virus. What type of virus it is? It is a virus that infects bacteria. Right? What is it? It's a virus that infects bacteria. So it is a hyperparasite. What type of parasite it is, students? It's a hyperparasite. What is a hyperparasite? Right? A parasite on parasite. Like let's say you people are parasite on me. Let's say Nandini is parasite on me, and Yashwini is parasite on Nandini. So Yashwini will be hyperparasite. Right? I am the host. Nandini is a parasite. Okay. Let's say Nandini is a bacteria, Nandini is a parasite. Now Yashwini is parasite on Nandini. So Yashwini will be hyperparasite. So what is the meaning of being a hyperparasite? That the parasite on a parasite. Right? See, something is having that capability. Something is having that someone is having that capability, that they can be a parasite on a parasite. Right? Just your siblings, they are parasite. Right? And let's say someone is parasite on them. Someone is parasitic to them. Okay? Done? So genetic material is DNA. The final proof was given by Harsha and Chase experiment. Right? So it is the transduction experiment or the blending experiment. So it will be done in 3 steps: infection, blending, centrifugation, and E. coli bacteria and T2 bacteriophage it was used for it. Right? Now when you talk about the bacteriophage, you know that, as I said, it's a hyperparasite. It's a virus that is going to infect the bacteria. You know, you remember its structure, right? This one is double-stranded. It is having double-stranded DNA. So when you look at the virus, you know that this outer hexagonal cover here is, what is it? Bache, it is the protein cover. It's the capsid. If you remember, it is the capsid. It's a protein cover. And here, what is this? This is the DNA, the genetic material. Now, what is my point here? Let's say I took this, like I picked up this virus for my experiment, right? And I started culturing it, obviously with the help of host, you know that. So I started providing it in two different ways. I provided it the medium, right? Like let's say I started growing this virus, and obviously we need the host for that virus. Now virus otherwise is a non-living thing outside the body. Outside the body it's something non-living. So let's say I took 2 approaches. In one approach I used radio labeled or radioactive sulfur, and in another one I used radio labeled phosphorus. Okay, phosphorus P32S35. This is the radio labeled isotope of sulfur, and that's the radio labeled isotope of your of your phosphorus. Is that clear? P32 and S35. That point clear, bache? Right? So simply you can say that it's radioactive, obviously. Radioactive sulfur, radioactive phosphorus. So now, sulfur is the part of amino acid. Do you know that? Sulfur is present in amino acids. Basically, sulfur will be there in that protein. Right? Right? Sulfur is there in that protein. I hope you remember my trick. My trick is CMS. Chief Minister, sir. What is our trick here? The trick is Chief Minister, sir. What is the meaning of this trick? C stands for cysteine. C stands for cysteine. M stands for methionine. M stands for methionine. And S stands for sulfur. So cysteine, methionine, they are sulfur containing amino acids, right? Cysteine, methionine, they are sulfur containing amino acids. They are sulfur containing amino acid. So if I'm going to use radioactive sulfur, okay, if I'm going to provide this bacteriophage radioactive sulfur, so it should be the part of protein. Yes, Vishal? It should be the part of protein. Yes or no? It should be the part of protein coat. So it will be there in the protein coat. Means in such viruses, the radioactivity will be there in their protein coat. Means their protein coat will become radioactive. Is it clear? Sure? 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 So now when I'm going to use the radioactive phosphorus P32. So P, this is the part of phosphate, am I right? This is the part of phosphate. So now in that case, what is going to happen? Yes bache, in that case what is going to happen? The radioactivity is there in the DNA. Yes, the radioactivity is in the DNA. So any doubt? Yes bacho, any doubt? So everyone just mention this trick in the chat section, the CM sir, right? Mention this trick in the chat section, quick. Everyone in the class, please mention this trick in the chat section. Yes बच्चे, Sure. So basically now after all this we have two type of bacteriophages, one in which protein coat is radiolabeled, another in which DNA is radiolabeled, right? In which protein coat is radiolabeled and another in which the DNA is radiolabeled, isn't it? Okay, so let's say in first experiment what will be done? Wait. Okay, that's the first step. So here it is S35. So that is the first step and that is known as infection. Okay, so in the infection what is going to be done? Right, these bacteriophages, they are going to infect the bacteria. Which bacteria it is? It is E. coli, Escherichia coli. Right, which bacteria it is? It is E. coli, it is Escherichia coli. Am I right? Right, so S35, it is S35, so infection. So what is going to happen here? Bache, that here, right, this cell, this bacterial cell will be infected. This is the first step, it is the infection. So it will be infected, right? It will be infected here. Clear bache? Yes or no? Right, so after that there will be the blending. What is going to happen in blending? The bacterial cells, they will be agitated in a blender to contact, right, to break the contact in between this virus and the bacteria. See, in general, you know what is going to happen. This bacteriophage has infected the E. coli, right? It means it will pass its DNA to E. coli. It will use E. coli's machinery and it will make its own copies. That is going to happen. It is going to make its own copy. In general, we know what is happening. The DNA will pass. But here they are conducting an experiment to check what is going to pass. They are not aware, right? Hershey and Chase, they were not aware that it is the DNA which is going to infect, right? They were checking it because they were confused in between protein and the DNA, right? But we know what is going to happen. Clear bache? So now, first step is the infection, second step is the blending. So now what will be done in this particular step? Here this bacteriophage and this bacteria, they will be agitated in a blender because we want to break the contact, right? Because when there is the first step infection, it means bacteriophage has infected the bacteria. So we will get to know that whether it is the DNA or the protein. Okay, whether it is the DNA or the protein. So second step is blending. So here in this particular step, what's our approach? Here in this particular step, what is our approach? What is our approach? We are trying to break the contact. Okay, we are trying to break the contact in between this bacteriophage and the bacteria. Okay, this is what we are trying to do. Okay, bache, this is what we are trying to do. Okay, and the third step is the centrifugation. So here in this third step, what will we do? We'll try to separate the content of virus and bacteria. Okay, so you know that when it is the centrifugation, as per the density, as per the weight, things will settle down. Yes, Chetu, Varun, Nandini, this is going to happen, that as per the weight, the things will settle down. Things will settle down. In general, we all know that bacteria, it is going to be, yes, when you compare bacteria and virus, whose molecular weight will be more? When you are going to compare bacteria and virus, whose molecular weight is going to be more? Whose molecular weight is going to be more? Obviously bacteria. So basically bacteria will be there at the base. Bacteria will be there at the base, at the palate. Yes or no? Bacteria will be there at the base, at the palate. Yes, and the viral content will be here in the supernatant, the lighter one, right? The heavy things will settle down at base, the lighter things will come up. So viral content will be here in the supernatant, right? So now after centrifugation, what they got, right, that when they used S35 isotope, then they saw that radioactivity was there in supernatant. Right, radioactivity, it was there in supernatant. What they observed? That radioactivity, it was there in supernatant. Okay, means it was not there with the bacterial content. That's what they observed. And in second set of experiment, what they observed? That the radioactivity is there in the palate. Right. So in the palate, if there is the radioactivity, if in the palate there is the radioactivity, right. There is the radioactivity. So of course, it is indicating that it is the DNA, right? It is the DNA which passed to the bacteria. It was the DNA which was passed to the bacteria. So that is how they concluded that it is the DNA which will, right? It is the DNA which is going to do what? Which will pass to the next generation. Okay. So bacteriophage, it is infecting this bacteria. The DNA will come inside, right? The DNA of bacteriophage will come inside. So you know that in second step what we have done, right? See, in first step it was the infection. Why? Because we want our bacteriophage to pass its, right, to pass its genetic material. Now in the blending, they immediately try to break the contact, right? It will be done to break the contact in between bacteriophage and virus, right? In between bacteriophage and virus. Why? Because we want to make sure that what is going to pass to the next generation. Now in the centrifugation, they just try to settle down the things as per their weight. And what they observed? No radioactive detected in cells. Radioactivity was there in the supernatant, because supernatant was showing the viral content. And here radioactivity was detected in the cell and no radioactivity was detected in the supernatant. Got it? So that's how they gave us the proof about the DNA as the genetic material. Any doubt? Bache, supernatant, Monisha, the lighter things, right, which is present above palate pe, there will be the heavy things na. Okay, so do you have any doubt? Okay, so if you have any doubt, please ask. If you people have any doubt, please ask. So after this, we will discuss the we are going to discuss the properties of genetic material, the RNA word concept, and finally the semi-conservative model of the DNA replication, and then the DNA semi-conservative model, its experimental proof, and then DNA replication. Yep. Any doubt? No? Yes, please ask your doubts. Okay, chalo. Next. So why do we say that it is the DNA which is the genetic material? DNA is a biomacromolecule, even protein is a biomacromolecule, even polysaccharide is a biomacromolecule, right? But why do we say that it is the DNA which is the genetic material? Obviously, it should have something special, right? There should be something which is, which is differentiating it from the others. Isn't it? There should be something in that DNA which is differentiating it from the others. So when you talk about the properties of the genetic material, right, it should be able to generate its replica. That is something very important. Students, try to relate, okay, try to relate it with biotech. In the biotech, when we discuss the vectors, this is what we used to say now, that they should have origin of replication. That is something very, very, very important in their case. Hai na, Nandini? That in the case of in the case of bacteria, in the case of biotechnology, when we discuss the vectors, that's what we used to say, that the vectors are something which are having the origin of replication, right? Allow me a minute, students. Yes? Yeah, that's what we discussed, isn't it? So that is why here also, when we are saying that genetic material, so genetic material is something which can replicate, okay, which can make its own copies. So that's why this is the important point. Then it should be stable chemically and structurally. Why stability is important? Because if it is not stable, then there are chances, and if it is reactive, then there are chances that it will react with other biochemicals and it will change its form, right? Structurally stable means that structure will stay for a longer period, isn't it? That structure will stay for a longer period, isn't it? So it should be chemically and structurally stable. The stability is important, because if there is no stability, the mutations, the changes will be very rapid, and that changes are not good, right? At that rate, that changes are not good. Okay, so it should, right? So it should be able to generate its replica. It should be stable and stable chemically and structurally, and moreover, it should provide the scope for slow changes. We are not saying that genetic material should always stay the same, no, but its structure should be stable, right? Chemically also, structurally also, chemically also. Why? Because we want changes. That changes are important, that changes will result in variations, but that changes should not be at a very faster rate, right, Niharika? That changes should not be at a very fast rate, right? The mutations should be there, but the slow changes should be there, okay? And then it should be able to express itself in the form of Mendelian characters. Remember Mendelian characters, the factors? Do you remember? Right, that factors, they exist in pairs. Do you remember that? Right, they are stable, they are discrete, so it should be able to express itself in that form, right? Now, why do we say our DNA is the genetic material? Why not RNA? Right, why not RNA? So see, genetic material should be stable enough not to change with different stages of life cycle, age, or with the physiology, right? Our physiology will change, it depends upon our routine, it depends upon many things, okay? So if DNA will not be strong, so it will change with all the stages of life cycle, right, with the physiology, and this is not something that we want. So it should be stable, first thing, okay? Then now let's compare the RNA and the DNA, because as I said, we have two things now. We have RNA also, we have DNA also. But we have completed the evolution chapter. I told you in that chapter also we discussed the RNA word concept, If you remember, there also we discussed the RNA word concept. I told you that some scientists, they believe that it is the RNA that came first, but yeah, some believe that it is the protein that came first, but actually it is the RNA, right? Actually it is the RNA. You know that this RNA, right, this RNA came first, and this RNA, it is a nucleic acid also, students. It is a nucleic acid also, plus it is having catalytic property. Why do we say that it came first? Because it is nucleic acid, right? It is nucleic acid, right? So nucleic acid means genetic material, plus it is catalytic also. So why do we believe that it is the RNA which came first? Because it is a genetic material also, and it can catalyze the reactions. Okay, that's why we consider it. That's why. And you know that when RNA is acting like the enzyme, right, we use the word ribozyme for it, right? We use the word ribozyme for it, isn't it? Isn't it? We use the word ribozyme for it. So RNA word concept, nucleic acid, that's what we are discussing. So now this RNA, with the time, from this RNA, DNA formed. Why? Because RNA being single stranded, right, Niharika? RNA being single stranded, it was chemically reactive, it was not so stable, right? It changes at a very faster rate. So with the time, because complexity is going to increase, so we want something more stable, so DNA came from the RNA. That is it, right? Now in general, though, we were talking about why DNA is the genetic material. So now we will draw that comparison also. See, the genetic material should be, as I said, structurally stable. Okay, so R-OH group present at every nucleotide in RNA is very reactive. You remember now? In the sugar, at second carbon, OH group is there. That OH group now, bache, because that RNA is having that OH group, because of that, it became very reactive, and it became very labile also. Its structure is not stable. It is easily degradable. Okay, that is important. It is easily degradable. है ना? It's a rhyme. The structure is not stable. It is easily degradable. Okay. Further, RNA is catalytic. Something which is catalytic means it is reactive. It is reactive. So DNA chemically, it's less reactive, structurally more stable, right? And among two nucleic acid, DNA is a better genetic material, right? Why? Because even in DNA there is thymine at place of uracil, and because of that it provides additional stability. It is not so reactive, right? It is not so reactive. So that's why it's not the RNA that we consider the DNA. So this comparison is telling us that why do we consider DNA. Clear, bache? Clear, bache? So no doubt both are able to mutate, but RNA mutate faster. It is unstable, mutate at a faster rate. So that's why, bache, the viruses having RNA genome, you know, viruses, if their genome, if they have RNA as their nucleic acid, then what's the problem? If they have RNA as the nucleic acid, what's the problem? That RNA will mutate at a faster rate. So if that RNA will mutate at a faster rate, this virus will change its form. It will become something else. Like in the case of COVID-19, okay, when we talk about the COVID-19, again and again, students, we say na that this variant, that variant. So how that variants form? How that variants form? That variants form because of mutations. Right, that variants form because of mutations. Okay, because of mutations. And because these RNA viruses, they mutate at a faster rate, that's why it became very difficult to figure out the antidote for them, right? The medicine to destroy them, it became very difficult, right? Because they got mutated, so their structural changes occur. Done, bache? So always remember, viruses having RNA genome and having shorter lifespan, okay, they mutate and evolve fast. They mutate and evolve fast. Done? Yes, bache, Vishal, what's your question? Okay, so now the next question. RNA, as I said, the first genetic material. So there is now enough evidence to suggest that essential life processes like metabolism, translation, splicing, they evolved around RNA, because we consider it as the first genetic material, right? So you know that it is a catalyst also. Okay, and RNA being catalyst was reactive, hence unstable. So this is what we have already discussed. Fine, 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 fine. So remember this line, bache. DNA being double stranded and having complementary strand further resist changes by evolving a process of repair. Right, right. You know, na, in DNA, this is what we discuss. Vishal is asking a question. Vishal, that is very interesting question. Please wait. Right, we will discuss the genetic code, you will get the answer, right? I don't want my students to get confused. Okay, so this point is very important, students, that because DNA is double stranded, right, it is having that complementary basis, so it has also evolved a mechanism of repair. So in that repair mechanism, if there is any base which is, you know, joined incorrectly, they can rectify that thing. That's why it is also advancement. It is also an advancement for the DNA. Okay, so just have a look of this image. Step 1, RNA forms from inorganic sources. Okay, from inorganic sources, this is how the RNA will form. Then RNA replicate itself via ribozymes. Fine. And in third step, RNA catalyzes protein synthesis. You know na, RNA helps in the formation of protein, mRNA forms the protein. So step 4, membrane formation changes internal chemistry allowing new functional. So basically these are kind of processes, right, that are telling us that central dogma of information, that with time how that evolution occurred, right, that with time how that evolution occurred. Clear, bache? Sure? Sure, sure, sure. So now let's talk about the different models of DNA replication and then let's move to the next topic. Any doubt? Okay. But overall, Jason, the DNA stores the information, right? That bases complementary to them. In the mRNA, further bases will be added. They are going to provide you the information. If you remember, Jason, both sugar phosphate backbone is present in DNA as well as in RNA. So, bache, how about this chapter? Like up to this part, what are you thinking? What are you thinking? Like, can you retain the things, or you want me to take 2 parts for this chapter, or yes, you are okay with the speed? We can even increase the speed and we can, you know, finish this chapter. What do you want? It is interesting, let me tell you. It's not boring. Okay, it is not boring. It's a conceptual chapter. Okay, if your concepts are clear, then there is no problem at all. It is a very interesting chapter. And that's the beauty of this chapter, bache. If concepts are clear, na, then wow. Then actually it is a wow chapter. So how many people think that it is a difficult chapter? It is interesting. Literally, it is interesting. Okay, thank you Manisha. Just a minute students. Okay, so let's talk about the models of DNA replication. So we have three models. One is the conservative model of DNA replication, another is the semi-conservative model of DNA replication, and then there is the dispersive model of DNA replication, right? Conservative, semi-conservative, dispersive. Conservative, semi-conservative, dispersive. These are the three models that we have. Understood? Now when it comes to the conservative model, okay, conservative models means to compare. See, first of all, even Watson and Crick, even they proposed it. When they were suggesting the base pairing, they proposed it that yeah, because bases are added complementary, so yes, it is possible that we can use one strand of DNA, right, as a template. What is the meaning of template? Template strand means the strand, right, which we are using to copy the information. What is the template strand? The strand that we are using to copy the information, that is the template strand, right students? That is the template strand. Clear? Clear. Now what is my point here? Even Watson and Crick, they proposed it, that yes, because adenine, you know that in front of adenine always thymine will be there, in front of cytosine guanine will be there, so yes, we can use that information. We can use the strands of DNA for copying the information. We can consider them as the template, right? We can consider them as the template. Are you getting my point? And if we will consider them as the template, okay, if we will consider them as the template, then obviously what is going to happen? We can synthesize the new DNA molecules. So there are different ways of, right, there are different ways of copying the information. Conservative it is, semi-conservative it is, and the dispersive it is. And the dispersive it is. Okay, and the dispersive it is. So when it is the conservative, it's very simple model, right? Ultimately these strands, right, they will open up as per this model also. The complementary to it, the new bases will be added. Complementary to it, new bases will be added. And finally, bache, what is going to happen? What is going to happen, bache? That, see, let's say this is the parental strand. Okay, this is another parental strand of the DNA. So complementary to it, new bases will be added. Two newly synthesized DNA strands will form. Two newly synthesized DNA strands will form, yes or no? Two newly synthesized DNA strands will form, yes or no? Yes or no? Okay, then what is going to happen, right? What is going to happen? That these parental strands, they will rejoin. Okay, these parental strands, they will rejoin, and these newly synthesized strands, they will also rejoin, because ultimately they are also complementary to each other. So when you talk about the two daughter DNA strands, when the model of replication is conservative model, so when you talk about the, yes bache, when you talk about the daughter DNA strands, yes bache, when you talk about the daughter DNA strands, right, so one will be ditto parental one, another one will be the newly synthesized, another one will be the newly synthesized. Clear bache? Clear bache? So here you can see the parental strand. So first replication, right? After first replication, one daughter strand will be ditto like parent and one will be newly synthesized. So when they will replicate, one will be ditto like parent, one will again synthesize. Here also one is parental, one will again synthesize. So conservative. So in the daughter strands, right, in the daughter generation, one DNA strand will be totally like the parental strand. Okay, totally like the parental strand. Now come to the semi-conservative model of DNA replication. Now next is what? Semi-conservative model of DNA replication. It is the next one. Okay, semi-conservative model of DNA replication. So here what is happening? Your DNA, right? Here what is happening? Your DNA will open slowly, right? Your DNA will open slowly, and complementary to it, right? Complementary to it, new bases will be added. So now what is going to happen here, bache? So here, when you talk about the first generation, the daughter generation, right, in the semi-conservative model of DNA replication, one strand will be the parental like, one will be the daughter strand. Like see, when this DNA will open, one will serve as a template, complementary to it, new bases will be added. Then these two strands, they will form the hydrogen bond, they will form one daughter DNA. These two strands, they will also join with the hydrogen bonds, they will form other daughter DNA. So in this way, what are we going to get? We are going to get the two daughter DNAs. What are we going to get, bache? We are going to get the two daughter DNAs. Okay, this is the conservative model. This is the conservative model of DNA replication. Now the next one is dispersive, right? The next one is dispersive. So now in the dispersive one, when you look at the daughter strands, bache, the parental DNA will be there, and in between the daughter DNA, parental DNA in between the new DNA, it will be like this. So this is going to be dispersive. And you know that what is the part of our syllabus? The semi-conservative. It is the most common one. Okay, it is the most common one. So if you have any doubt, do let me know. So see the dispersive. So blue, yellow, yellow. Yellow is the newly synthesized, right? Blue is the parental one. Any doubt? Yes. Bache, if you will just chit chat here, I will end the class, right? I'm not going to give you any warning, Mr. Blue, Vijay Kumar. I will directly end the session. Okay, I will just end the session if you will not stop chit chatting here. Okay, so let's talk about the DNA replication. Clear, bache? Let's talk about the DNA replication. Okay, so as I said, the scheme suggested that two strands would separate. They will act as a template for the synthesis of new complementary strands, right? Two strands, they will separate and they will act as a template for the synthesis of new strands. Is that clear? For the synthesis of new strands. Is that clear? These strands will open, they will act as a template. Template means something from where we can copy the information. Okay, and then what is going to happen, bache? The new bases will be added. So after the completion of DNA, each DNA molecule would have one parental and one newly synthesized strand. This is the semi-conservative mode of DNA replication. Clear, bache? So again I am repeating, who proposed the semi-conservative model of DNA replication? Who proposed the semi-conservative model of DNA replication? Tell me. It was proposed by Watson and Crick. Right, there is a paragraph written there in NCERT. So it was proposed by Watson and Crick. So if in the paper, if in the final paper Niharika, they are asking who proposed the semi-conservative model of DNA replication, that is Watson and Crick. But if they are asking for the experimental proof, so who gave the experimental proof of that semi-conservative model of DNA replication? Matthew Michelson and Franklin Stahel. Matthew Michelson and Franklin Stahel. Right, in 1958. So Matthew Michelson and Franklin Stahel in 1958, right? So they performed this experiment. Is that clear? They performed this experiment. Thank you, Satya. Please focus here. Okay, clear, 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 clear. Okay. Okay, done. So who gave the experimental proof? Matthew Meselson and Franklin Stahel. So bache, when you talk about the Matthew Meselson and Franklin Stahel, they experimented on E. coli. Okay, so it's not just the Matthew Meselson and Franklin Stahel, right? People, they also performed experiments on eukaryotic cells, on the higher organism. Like we have Taylor and colleagues, right? We have Taylor and colleagues. They experimented on a plant. Plant means eukaryotic. Okay, plants means eukaryote, right? On the faba beans. Okay, that is Vicia faba. They experiment on Vicia faba, and that is basically known as faba beans. Okay, faba beans. And what they use? They use the radioactive thymidine. What they use? They use the radioactive thymidine. Is that clear? Radioactive thymidine. Clear bache? Clear bache? So Meselson and Stahel 1958, Taylor and colleague, they also performed it right on Vicia faba, and they used the radioactive thymidine. So now let's discuss the experiment of Matthew Meselson and Stahel. Right, let's focus there. So first of all, what they did, see, we know that in our DNA we have nitrogen. Yes, DNA is having the nitrogenous basis, so it means we have the nitrogen. Yes or no? It means we have the nitrogen. Yes or no? Of course. And naturally this isotope of nitrogen is present, N14, isn't it? Naturally it is the N14 which is present. Am I right or wrong? It is the N14 which is present. Am I right or wrong? Of course, it is the N14 which is present. Now what is the next step here? Clear bache? What is the next step here? Now when you talk about their experiment, right, they took E. coli, right, they started growing it in a culture, right, they started culturing E. coli. Okay, now you know that for the cultures we have to provide the culture medium, which is basically the nutrient medium in which that E. coli is going to grow. Yes or no? So they took E. coli, your Escherichia coli, and they started growing that E. coli in a culture medium, right, in that nutrient medium, in that culture medium. What they provided? They provided E. coli the 15N isotope of nitrogen, right, 15N. But check this N14, which is naturally occurring. It's a light isotope of nitrogen. It is not heavy. Okay, it is light isotope of nitrogen. And when you talk about N15, it is the heavy isotope of nitrogen. Always remember, please always remember this thing. Always remember this thing. It is the heavy isotope N15. It is not radioactive. That's the most common mistake that you used to make. Even it is given in NCERT. Right? Even it is given in NCERT. So N14, what is N14? N14 is the light isotope of nitrogen. N15 is the heavy isotope of nitrogen. Clear? It is the heavy isotope of nitrogen, right, bache? So you can see here E. coli, and it is the heavy isotope of nitrogen. Is that clear? It is the heavy isotope of nitrogen. Now when they started growing E. coli in the culture medium, they allowed it to grow for many generations, and as I said, they provided N15. And how as ammonium chloride, it's NH4Cl, it's 15 NH4Cl, right? It's 15 NH4Cl that they provided initially. So let's say if I will allow you to grow in a particular kind of environment, right? Since your childhood, let's say you are in a particular type of environment, obviously your thinking will also be like that, right? If you start living in a, let's say from your childhood you are in a conservative family, you're the part of a conservative family, you don't have any contact with anyone else, obviously you will also start thinking like that, right? Even your universe will be limited to that particular family only, isn't it? Of course, है ना? Now here, when I picked up E. coli, right? I wanted that E. coli to have N15 only, right? I wanted that E. coli to have N15 only, to have heavy isotope of nitrogen only. So I started growing that E. coli in a culture medium where I'm providing ammonium chloride with heavy isotope of nitrogen. Then when I'll be sure, right? When I will be sure that when you talk about the DNA here, right? When I'll be sure that here in E. coli the DNA is having 15N, so I will take the E. coli cells. Now I will shift that E. coli to another culture medium, right? To another culture medium, but here I am providing 14 NH4Cl. Basically here in this culture medium I am just providing light isotope of the naturally occurring isotope of nitrogen to the E. coli. Okay. So now bache, when you people talk about E. coli, right? When you people talk about E. coli, that is your Escherichia coli. That is your Escherichia coli. When you talk about this now, then what is the point here? What is the point here? Yes, what is the point here in this E. coli? But E. coli's generation time is 20 minutes. Like in some books in NCERT also 18 minutes is given, na? 18 minutes is given roughly. So basically E. coli's generation time is 20 minutes. Right? E. coli's generation time is 20 minutes. What is the meaning of generation time? Means it will replicate into its daughter cells in 20 minutes. Okay, so one cell will start making 2 cells after 20 minutes. So after next 20 minutes you will get 4 cells. After next 20 minutes you will get 8 cells. Is that clear? So what is the generation time of E. coli? Everyone in the chat section, quick. Everyone in the chat section, quick. What is the generation time of E. coli? What is the generation time of E. coli? Yes? Okay, so now here in this culture after 20 minutes, right, Messelson and Stahel, they isolated the E. coli cell, right? They isolated the E. coli cell. Now what are they trying to do? They just want to check the DNA, the density of DNA, right? They use the cesium chloride density gradient. What they used? Cesium chloride density gradient. This is another important PYQ bache. It is cesium chloride density gradient. What is it? It is cesium chloride density gradient. Clear bache? Clear bache? So basically they are going for the ultracentrifugation. Now it's very simple bache. Whenever we conduct any experiment, we always used to have a control, right? Whenever we conduct any experiment, we always used to have a control, right? We always used to have a control. Like control means, let's say I want to see what we have done, that we are making our DNA heavy and the lighter one. Why? Because we want to confirm semi-conservative mode of DNA replication. So initially what am I going to do first? If I have to conduct this experiment, I will obtain that bands separately as per their weight. So 15N is heavier, its band will form here near to the base. 14N is lighter, so obviously its band will be above, right? It should be like this. Now what I did here, that after 20 minutes bache, I isolated the DNA, right, from the daughter cells of the E. coli, and I performed the centrifugation. I use the cesium chloride density gradient. Cesium chloride density gradient. This is another MCQ. So I obtained the band, and you know I got the band somewhere in between. It was not the heavy like 15N. It was not the lighter like 14N. Okay. Let's say this is the case now. So after first generation, the band that I obtained, it was somewhere in between this, right? It was somewhere in between. It was just like hybrid. It was not heavy, it was not lighter. Okay, it was not heavy, it was not lighter. Are you getting it? That's how I obtained the first band. So I obtained it after 20 minutes of that setup, right? After 20 minutes. So after next 20 minutes, means in totality after 40 minutes. Let's say you started the experiment at 8, right? Then you will obtain the daughter cells or their DNA at 8:20. Then after 8:20 you will obtain it at 8:40. Then after 8:40 you will obtain it at 9. It's like that, right? It's like that, right? So what is going to happen? Just have a look. Initially the DNA was heavy, right? 15N. So this pink color is showing the heavy isotope. Okay, pink color is showing the heavy isotope. So after 20 minutes, what is the scenario? What is the scenario? That is the scenario. So after next 20 minutes, what is going to be the scenario? This, right? This pink wall will open, and the new, because white is showing 14N, okay, white is showing 14N, so it will be like this, right? After next 40 minutes, right? So this is hybrid. It is having 115N, 114N. So it is telling us semi-conservative mode of DNA replication. It is telling us that DNA strands will open, complementary to them new bases will be added, and then that parental strand and the new strand will join, and that's how we are going to get the daughter DNAs. Okay, that's how we are going to get the daughter DNAs. Okay. So that is what we have at the end. That is what we have. Okay, so they checked these bands, they checked that experiments again and again. So that is how they proved that yes, it is because the presence of hybrid is indicating semi-conservative mode here, right? One is heavier, one is lighter, that's why. Clear? Any doubt? Yes. Do you have any doubt here? Please tell me, do you have any doubt here? Sure? Sure? So that's what you need to remember, okay? That's what you need to remember. Fine. So let's read it from, okay, done. That's what you need to discuss. So let's revise it from the NCERT. So see, red color is showing 15N DNA. So its band is at the base. Okay, its band is at the base. Why? Because it is heavy. Okay, because it is heavy. Clear, bache? So they use the centrifugation in cesium chloride density gradient. Clear? So after 20 minutes, this is the hybrid, right? Green is showing 14, red is showing 15. It is the generation 1. Then in generation 2, right? Why? In generation 2, two hybrids are there. Two are having 14 and 14N only. Why? Because now in the medium only 14NH4Cl is available. Okay, 14NH4Cl is available, that is why. Clear? So very similar experiment involving the use of radioactive thymidine to detect the distribution of newly synthesized DNA in chromosome. It was performed on VCF Faba, right? Faba beans. It was performed by Taylor and colleagues in 1958. Okay, so that's what you have to remember. So any doubt? Yes. Any doubt? Because next topic that we are going to discuss is your DNA replication. So that is a lengthy topic actually. That is a lengthy topic. So tell me, any doubt? Any doubt? Sure? Are you sure? So what do you know about the DNA replication? Yes, tell me what do you know about the DNA replication. Aaron, let's finish the DNA replication, then we can talk about the break. So you want the break for 5 minutes? Okay, Monisha. ठीक है. So if there is any doubt in between, you please ask. If there is any doubt, do let me know. Done. So can we continue? Yes, can we continue? Okay. See, bache, that's my advice, right? That in molecular basis of inheritance, whatever processes are there, whether it's replication, transcription, translation, whatever it is, please do one thing. Remember it like a story. Okay? Okay? Remember it like a story. In the form of a story, try to remember it. Right? Do not be like, yaar, chalo, let's cram the topic, let's do it in this way, that way. No. Just take it like a story, that it is a story, and you are, learning. And imagine the DNA, imagine the double helical model, imagine the enzymes, and imagine how that enzymes are working. That's what you have to do, right? That's what you should do. Okay, so in that way the topic is going to be really easy for all of you. So the topic is DNA replication. You know that we have interphase as well as M phase, right? Interphase as well as M phase. So now in interphase we have G1 phase, gap 1 phase, synthesis phase, gap 2 phase, and M phase is the actual division phase. Now whenever we talk about the DNA, okay, we know that in the S phase there is the DNA replication, there is the DNA synthesis, there is the DNA duplication. That's what we study, right? That in the S phase there will be the duplication of DNA, right? The chromosome number will remain same. Like let's say if a cell is having 2C, C is used to denote the concentration here, right? If 2C is the concentration of the DNA, after S phase it is going to be 4C, right? After S phase it is going to be 4C. 2C will become 4C. That's what we know, right? G1, S, G2 and M phase is of division. So 2C will become 4C, right? 2C will become 4C. That's what we know. So now how that replication is taking place? We know that when it comes to the DNA, right? Why is it a genetic material? Because of its property of replication. It can replicate, it can make it multiple copies, and that's what we need to imagine. That's what we need to think. So in S phase all that process is taking place. Okay, in S phase all that process is taking place. So now you know that we have two types of cell. One is your prokaryotic cell, or prokaryotes you have, and another is your eukaryotic cell, and we have eukaryotes. One is the prokaryote, another is the eukaryote. One is the prokaryote, another is the eukaryote. So now when you talk about the prokaryotic cell, you know that the DNA is directly there in the cytoplasm. Here we know that in a nucleus the genetic material is present, right? And in both the cases DNA replication will be there. So bache, in our syllabus mainly it is the DNA replication of E. coli. We mainly discuss the replication of E. coli. That is the part of our syllabus, right? So basic procedure is same in both the cases, but yeah, there are few differences. Clear? There are few differences, but basic procedure is same in both the cases. Clear? So are you ready for the story? Then we will read that story from NCERT. So one thing is clear to us, Niharika, that it is going to be semi-conservative mode. And students, I'm not going to teach you this in this space, right? First of all, tell me, are you all feeling good, energetic? Yes, excited, right? I want to see that, yeah. I want to see that reactions in chat section, right? I really used to appreciate this channel, that we just have good crowd. We do not have people who came here for the chit chatting, but now we have students, those who are just using this as a, you know, as a platform to chat. So everyone, please block them. Okay, if you all will block them, automatically they will get blocked. Quick bache, let's discuss this topic. Right, for sure you will get a question from DNA application in your NEET examination. For sure you people are going to get. You people are going to get it. Quick. Yes, so are you ready? So should I start? Sure? Okay, so we know that the process is going to take place in S phase, right? That's what we know. We know that the process is going to take place in S phase, right? The DNA application. So what should be the first step? Of course, if I talk about the requirement, we will be needing DNA, of course, and the certain enzymes, right? And we need certain enzymes. So you can note down the name of that enzymes, helicases, right? Also known as unbindase. We need single stranded binding proteins. Write down the requirement. Right, single stranded binding proteins, that is SSBP, single stranded binding protein. Then bache, helicase, single stranded binding protein we have. Then what do we have? Topoisomerase. That is your DNA gyrase in the case of prokaryotes. We will discuss that too. Then we have DNA polymerase. Okay, that is also the part of requirement. DNA polymerase. So that we will discuss later. We are having DNA ligase also and the primase also, right? And the primase also. That's what we need for this process. It's DNA dependent RNA polymerase. Okay, DNA dependent RNA polymerase. Clear? Is that clear? Sure? Yes, even the ligase, Krutika, even the ligase. So, helicase, unbindase, single-stranded binding protein, topoisomerase, DNA polymerase, DNA ligase. That's the requirement. Yes, and of course, magnesium ions are also required. Right, magnesium ions are also required. ATP is also required. Right, DATP, DGTP, DCTP, DTTP, they all are required. Fine, they all are required. Now what is going to happen? Let's start in the case of prokaryotes. So prokaryote is a bacteria, right? Prokaryote is what? Prokaryote is prokaryote is what? It's a bacteria, right? Bacterial cell. They are the prokaryotic cells, and we are taking the example of, yes everyone, please write it down in the chat section. We are taking the example of E. coli, right? We are taking the example of E. coli, isn't it? So here you have the nucleoid, right? And it is the circular DNA, right? It is the circular DNA. We have the nucleoid, and it is the circular DNA. That is what we have. Okay, understood? Is that clear? Now what is the next point here, right? What is the next point here? Now it's a circular DNA. I need to start the replication. Do you think that I will go somewhere and I will start my process? It's not like that. It is not like that I will look at the DNA and I'll be like, okay, I want to start the replication, let's do it. No, not at all. Not at all. I want a proper point from where the replication can start. Right, the point from where replication can start. Okay, point from where the replication can start, and that is going to be origin of replication. What is it? That is going to be origin of replication, and that is the ORI site. That is the ORI site. ORI, origin of replication. It is the point from where the replication can start. Right? Right? Now in the case of prokaryotes, because it is a circular DNA, what type of DNA is there, students? It's a circular DNA. So here in this DNA there is only one origin of replication, one ORI site, and that is ORIC. What is the name of that site? ORIC. Right? So there is only one origin of replication site. There is only one point from where the replication will start, right? So that is why prokaryotes are monoreplicant. Monoreplicant means the single point from where the replication will start. Replicon, the place from where the replication will start. Is that clear, everyone? Just let me know. Imagine you have a cell, you are having a DNA, the circular DNA is there. Now you want to replicate that DNA. So you are looking for a point. And what do you think? Who's going to provide that? Who's going to figure out that from which point the replication need to be started? 110%, that is going to be the proteins. But luckily that proteins are not the part of our syllabus, right? Like when we start this process, we talk about the DNA-C, which is a protein, which is an enzyme, which is going to figure out which origin of replication, that where is origin of replication, but that's not the part of our syllabus, so we are skipping that point. Is that clear? Right? Is that clear? So first point clear, right? Done and dusted. Sure? Sure? Is it done and dusted? Yes? Is it done and dusted? So prokaryotes are polyreplicant or multireplicant? Prokaryotes are polyreplicant or multireplicant? Yep. Prokaryotes, are they monoreplicant or are they multireplicant? Of course they are monoreplicant. Okay, but on the another hand, bache, eukaryotes, but they have linear DNA. In the eukaryotic cells, the linear DNA is there, very long DNA it is. So in their case, there are many points from where the replication can start. So you are going to call it as multireplicon, right? You are going to call it as multireplicon. Understood? Okay, so what is the next point here? Okay, that's it, that's done. So what is the next point here? Okay, we obtained the so now we know which one is the origin of replication. So it is a circular DNA. Can we take this diagram as of now? Can we take this diagram as of now, that let's say it is a circle. It is a circle. This is the point from where the replication will start, right? Okay, so do you think we can start the replication like this? No, of course not. I have to open up the DNA, right? We have to open up the DNA, then only we can read the information given there. We cannot directly start the replication. We have to open up the DNA. What we have to do? We have to open up the DNA. So imagine this is your DNA. You are trying to open it up. Can you just open it in one go? No. Why? Why? Because it is very energetically very expensive. It takes a lot of energy to open the DNA. For opening the DNA, you have to break the hydrogen bond. Are you understanding it? Guys, do not cram. Understand. Okay, okay, like let's say this is your okay, so this is your highly coiled DNA, right? You are trying to open it. You are trying to open it like this. So it is going to be energetically expensive. You have to break the hydrogen bond. It takes a lot of time. Fine. So for opening this, we need one enzyme, and yes, you are right. That enzyme is helicase, also known as unbindase. Okay, and this particular enzyme will use magnesium as cofactor, and moreover it needs energy from ATP. So with the help of ATP hydrolysis, right, it needs the energy from ATP. ATP hydrolysis is also required. So with the help of that, right, slowly it is going to open the DNA strands like this, like this. Just let's say let's say magnesium is the cofactor, Akshita, cofactor for the enzyme, right? So now let's say this is your helicase, it is coming up. It will not open your DNA like this immediately. No, it can do this, but slowly, very slowly, because it will take energy. So obviously, don't you think that you are going to get a structure, Y-shaped structure? Can you see that it is Y-shaped structure? Yes, right? If I take my DNA like this, one strand having polarity 5' to 3', another strand having polarity 3' to 5', so helicase is going to open it up very slowly. So what are we going to get? We are going to get the Y-shaped replication fork. What type of replication fork? Y-shaped replication fork, right? Y-shaped replication fork. So is that clear? Is that clear? So it will not be in one go, slowly. Now you know that DNA, these bases will try to re-anneal, right? These two strands, they are separated, but they will try to, they are, right, I am separating them, but they will try to rejoin, they will try to re-anneal, they will again try to join. Why? Because when they will join, that stability will be there, no? Right? They are complementary to each other, so they are like, array, quickly let's join. It is the, but we don't want them to join. Why, Leia, Krutika, Aaron, why? We don't want them to join. We really don't want them to join. The reason is we want to copy the information from these strands. So obviously what is going to happen? Single-stranded binding proteins are going to play the role now. Which proteins are going to come now? Right, first step clear, the helicase step clear and its usage clear. Second is your SSBP, single-stranded binding proteins. That single-stranded binding proteins will prevent, they will stop re-annealing. What will they do? They will stop re-annealing of this DNA strand, right? They will not allow the DNA to rejoin, to re-anneal, so that it will be available for us to copy the information. Okay. Now, don't you think that our DNA is circular? Like, let's say if this is the origin of replication, if this is my ORI-C site, I am trying to open it here. So is it possible that in both the direction I can copy the DNA? Is it possible? We are talking about the E. coli now, na? I am saying it's a circle. Is it possible that in both the direction I can copy the DNA? Yes, it is possible. And in E. coli, there is the bi-directional. The replication is bi-directional. Like, this is the point from where the DNA will open. So it will be replicated in this side also, towards this side also. So that is why its generation time is 20 minutes. If there will be the single direction of replication, then its generation time will be more. Right? Then its generation time will be more. It is double-stranded, bache. It is double-stranded. So both the sides, right? So replication will be there in both the sides. Now, okay, fine, ma'am, theek hai, acceptable. Okay, acceptable. But why are you telling this to us? What is the point here? I have a very simple point. So when my helicase will come to open up the DNA, you know my helicase is going to form the Y-shaped structure. And you know that helicase is not going to break DNA, right? It's not like that helicase is going to make a cut like restriction endonuclease and going to straighten up the circular DNA. No, big no. Okay, it's a big no. Okay, so it will just open it, because now direction, right? Because now replication is in both the directions. So here it is the replication bubble. What is it? It is the replication bubble that will form. What is it, students? It is the replication bubble that will form here, right? It is the replication bubble, because in both that. So now what exactly is the replication bubble? Try to see it here. It's something like this, है ना? It's something like this. That is the replication bubble. Like if I will put it like this, this is the replication bubble. So I can say, right, if you will see this part only, right, this is one Y-shaped fork. If you will see lower part only, this is another Y-shaped fork. So can I say that in a replication bubble, it is actually two replication forks? Why? Because replication is going on in both the directions. Replication is going on in both the directions. So can I say that? Can I say so? If you cannot understand, imagine it in this way. That's my bag, Sava. That's my bag, right? This is the origin of replication. Okay, students? This is my bag, and here I have the origin of replication. Can you see that? So now the replication is going on in both the directions like this. In both the directions it is going like that. So if I will try to open up this zip, right, with the one zip only, so I have to move it like this. If I will start from the center and if I will move it like this, I'll open it up early, na? Even if there is a difference of few milliseconds, but still that's a fact. So same is the case here, right? Let's say this point is the origin of replication. This point is the origin of replication. From this origin of replication in both the directions, right, the strands will be copied. The replication is going on. So here when helicase will come, when helicase will do the unbinding, right, so you will get the replication bubble. What will you see here? You are going to see the replication bubble, right? What will you see here? You will see the replication bubble, and that replication bubble is having two Y-shaped replication forks. Now clear? Now clear? Now clear? Sure. So in E. coli it is going to be bidirectional. Even in the eukaryotes also you will see it like this. Is it clear? Are you sure? 110%. The Y-shaped replication fork part clear? So we will pick up only one side, of course, because we are not that smart, no? We can understand it in both the directions. So helicase will not open the DNA in one go. It will do it slowly because it is taking a lot of energy. Okay, it is taking a lot of energy. Okay, so now to these single strands, what is attached to these single strands? The single stranded binding protein, because they will not allow the re-annealing. They will stop the re-annealing. They will not allow these strands to join again. Now when you try to open something helical, when you people try to open something helical, like I have something like this. Yes, people, I have something like this. Okay, I'm trying to open it up. See, I'm trying to open it up. The tension will be created here, no? The tension will be created here, no? Here. See, I cannot move my DNA. Sorry, I cannot now open it up because of this tension. You can try it at your home. I'm trying to open it up, but I cannot because of the tension. Right, because I'm trying to open the helically coiled DNA. So a coiling, some coilings will be there that will create that tension. Okay, and my helicase will not be able to work smoothly. My helicase will not be able to move ahead. It will not be able to open up the DNA. So in that case, I have another enzyme that will help me. Right, I have the enzyme that is going to help me. The name of that enzyme is topoisomerase. What is the name of that enzyme? That is topoisomerase. So it removes supercoiling. It is the one which is going to remove the supercoiling. right bache? It is the one which is going to remove the supercoiling. It removes the supercoiling, right? It will cut the DNA strand. It will remove that tension. It will rejoin them, right? So that helicase can move slowly. And this topoisomerase is having two classes, class 1, class 2. Class 1, class 2. Class 1 will make cut in one strand of DNA only, and then obviously will try to remove the tension. Class 2 enzymes, they cut both the strands, they remove the tension, they rejoin the DNA. Clear? So now in prokaryotes, clear bache? Now in prokaryotes, okay, right bache? In prokaryotes, it is the DNA gyrase, fine, it is the topoisomerase. In prokaryotes, basically the first identified topoisomerase is DNA gyrase. It is the class 2 topoisomerase, means it can cut both the strands of DNA, it can remove the tension, right? So in prokaryotes, the topoisomerase is known as Swati. In prokaryotes, the topoisomerase is known as DNA gyrase. The topoisomerase is known as DNA gyrase, and this DNA gyrase, it also needs ATP hydrolysis, right? It also needs ATP hydrolysis, right? So in eukaryotes, you will not use the word DNA gyrase. In prokaryotes, you are going to use the word DNA gyrase. It is nothing but the topoisomerase. Understood? So in prokaryotes, topoisomerase is named as, topoisomerase discovered is known as exactly. Okay, so that's how my helicase will move and it will do its job. So now both the strands are acting like a template. Which strand is template? Which is giving us the plot so that we can, add the bases and we can make the new strand. So look at these two template strands. So this template strand is having polarity. This template strand is having polarity. Yes, this template strand is having polarity. Can you tell me the polarity of this template strand? This is how the helicase is moving, and that is how the new bases will be added. So the polarity of this template strand is, the polarity of this template strand is 3' to 5'. Yes, it's 3' to 5'. 3' to 5' now. So please do not, Samiksha, do not be confused. It's not like that 5 to 3. No, right? You are opening your DNA from this side. So this side you are going to consider 3' to 5'. Now what about this strand? This strand is having the polarity. This template strand is having the polarity 5' to 3'. Right? This template strand is having the polarity 5' to 3'. Is that clear? Is that clear? These 2 points clear? 3' to 5', 5' to 3'. Understood? Now we know that when it comes to the replication, the main replicating enzyme is DNA polymerase. You know that it is the main replicating enzyme. It is the one which is going to replicate the DNA, right? In prokaryotes, there are 3 DNA replicating enzymes: DNA polymerase 1, DNA polymerase 2, DNA polymerase 3. And this polymerase 1 is also known as Kornberg enzyme because it is discovered by the scientist Kornberg. So it is also known as Kornberg enzyme, right? So what are we talking? We are talking the story of the DNA polymerase, the main replicating enzyme. So I am telling you that when you people talk about the DNA polymerase in the prokaryotes, there are 3: DNA polymerase 1, DNA polymerase 2, DNA polymerase 3. So bache, it is the 3 which is the main, which is the main replicating enzyme. It is also known as, do you know that? It is also known as replicase. It is also known as replicase because it will copy the DNA. Okay, it is going to copy the DNA. And DNA polymerase 1, it is known as Kornberg enzyme. It is known as Kornberg enzyme, discovered by the scientist Kornberg. So DNA polymerase 3. Which one? DNA polymerase 3. That is the main replicating enzyme. Is that clear, everyone? Is that clear? That is the main replicating enzyme. So it is the story of prokaryotes. Fine. So remember, in eukaryotes it's different. In eukaryotes, right? It's not the part of syllabus, but you should know. There will be DNA polymerase alpha, beta, delta, epsilon, like this, right? In eukaryotes you do not have, right bache? In eukaryotes you do not have the DNA polymerase 1, 2 and 3. There you are going to have DNA polymerase alpha, beta, like this. Fine, like this. Clear, clear, clear. So we have in prokaryotes, what do we have? We have 3 replicating enzymes: DNA polymerase 1, DNA polymerase 2, DNA polymerase 3. So this third one is the main replicating enzyme, and other 2, they are going to play a role in the DNA repair, right? And other functions are also there. So tell me, up to this part all clear? Up to this part all clear? Right? So can you imagine your DNA? You are opening up your DNA with helicase. You don't want the strands to bind with each other. You want to prevent their re-annealing. You are using single-stranded binding protein. Meanwhile, because of some tension, helicase cannot move. So you are using DNA gyrase, and that gyrase will remove the tension and further helicase will move. Now we have to add the complementary bases, right? We need to synthesize the DNA. So we know which enzyme it is. It is the DNA polymerase 3. It is the DNA polymerase 3. Which enzyme it is, students? It is a DNA polymerase 3. That is the main enzyme. Now, how is it going to work? See, I will tell you the function of 1 and 2 as well. But later, first of all, let's talk about the DNA polymerase 3. Right? I will tell you about the function of DNA polymerase 1 and 2 as well. But as of now, mainly focus on DNA polymerase 3. Understood? Understood? Okay. So that's your DNA. That's the Y-shaped replication fork. That's our DNA and that's our Y-shaped replication fork. Again, I am repeating the same point. Okay, again I am repeating the same point. Please understand it, and after it even the transcription, translation, everything is easy. Okay, so please understand it. After it I will give you the break as well. Okay, I'll give you the break as well after finishing this topic. So this is the Y-shaped replication fork. So the template strand here is having polarity. Please repeat this point with me. The template strand is having polarity 3' to 5'. This template strand is having polarity 5' to 3'. So now we know that our main, right, our lead actress is DNA polymerase 3. That has to add the bases. But this lead actress is having many issues. This lead actress is having many issues. You know, it is having many problems, right? This is superstars, they have that attitude problem, na? Aise kaise, hai na? Same is the case here. Now DNA polymerase 3 is aware that I am the main replicating enzyme. I am the one who's going to make the new DNA. So it is also having some issues, some attitude problem. The very first attitude problem is DNA polymerase 3 is like ki I cannot, it cannot initiate DNA replication by its own. Huh, ma'am, then what is the use of DNA polymerase 3? Hai na? Hai na? You must be thinking that ma'am, then what is the use of DNA polymerase 3 if it cannot initiate DNA replication by its own? It is not like something ki, okay, fine, I will do it. No, no. Like I'll give you one example. I'll give you one example. The example is, you cannot clean your room. You cannot clean your mess. Let's say your room is very tidy, very dirty, very bad. Okay, it's filthy. You people are filthy. You don't know how to keep the clean room and all, whatever it is. So you cannot start the cleaning of your room, right? But now you know your mother is inside the room. You know your mother has started the cleaning. For your safe side, what will you do? You will join her, na? If you are not that stubborn, hai na? If you are not that stubborn, if you don't have that guts ki theek hai yaar, she's going to say some words, na, I will listen to her. Right? What will you do? You will be like, Mama, Mama, I'll help you. And then what Mama is going to say? Mama is saying, then why can't you initiate it? Hai na? Hai na? Now I started, now you join me. Hai na? This is something we know. We all know. Right? Right? This is a story of our India. Indian moms are like that only. Hai na? Indian moms are like that only. So, DNA replication, DNA polymerase 3 is also the same. It cannot initiate the replication by its own. Why? Because it requires it needs 3-OH and then it can do the elongation. Then it can add bases. It can further add bases. Like, it is not something, right? DNA polymerase 3 is not like that. Oh my God, I will add the bases, right? And let's make the DNA. No, not at all, right? DNA polymerase 3 will not come up. Okay, fine, let's start the bases. No, it is like, Ale, someone please give me 3-OH. If I'll get 3-OH, I will start adding the bases. It's like that. It's like that. So obviously now we need another person. Now we need another enzyme. है ना? Now we need another person. Now we need another enzyme. And what is that enzyme? R primase. Now Miss Primase will come. Miss Primase will be like, oh my God, DNA polymerase 3, I have to come first. I have to add the bases. I have to make the RNA primer. And then you will use my RNA primer's OH. And then you will add the bases. How bad? But literally that's how it is going to work. Literally that's how it is going to work. It is having the issues, bhai. It is having that attitude issues. Oh, I cannot do such roles. I want the roles, the good roles, the lead roles. I cannot be the side artist. So primase will come. Now what that primase will do? Primase, right? Primase will form RNA primer. Bache, initially if you noticed that I mentioned this primase as DNA dependent RNA polymerase. It is DNA dependent RNA polymerase. That's the word that I used. DNA dependent RNA polymerase. DNA dependent RNA polymerase. So what is my point here? My point here is that this is the enzyme which will use the DNA template, and then complementary to it, it will add the RNA bases. It is going to add its RNA bases. RNA bases means the ribose sugar is there. So what is it going to form? It will form RNA primer. So it is 15 to 20 nucleotide long RNA. 15 to 20 nucleotide long RNA it is. Right? Now let's say, Niharika, I have added, and this primase is not like that. Primase is like, okay, fine, I can start the work by my own. Right? I don't have any need for OH or something. So now you have the primer. And as I said, the synthesis is always in direction. Ashmit, the synthesis is always in direction. The synthesis, Chetu Bachche, it is always in direction 5' to 3'. It is always in direction 5' to 3'. So if this template strand is 3' to 5', so complementary to it, the new strand will be synthesized, and that will be 5' to, that will be 5' to, yes, that will be 5' to 3' of course, right? So now, because see, I added one base, second base, third base, fourth base. Okay, so obviously one of the base, it's 3' end. Let's say it is the RNA primer. This end will have 3' end will have OH. The 3' end will have OH. The 3' end will have OH. And now DNA polymerase 3 will be like, oh my God, oh my God, oh my God. I got the OH. I got the OH. And that DNA polymerase will keep synthesizing the DNA now. Then it can add the bases. Then it can further do the elongation. So DNA polymerase 3 cannot initiate the DNA replication by its own. It needs 3-OH. It needs 3-OH. Understood? Understood? So let's say if here adenine is there, which base will be added here? If T is there, if C is there, if G is there, tell me which bases are going to be there? Complementary to A, Nandini. Complementary to A. Guys, be quick. Thymine. Complementary to T. Complementary to T. Very good. A, G or C. That is what we are going to get. Right? That is what we are going to get. But now this DNA polymerase 3 is having another problem also. Now this DNA polymerase 3 is having another problem also. But that's not the story. Ki polymerase, see, DNA polymerase 3. First of all, tell me, that is the direction of your replication fork. Niharika, that is the direction of your application fork. Sabha, I'm taking all the questions. That is the direction of replication fork. The replication fork is moving like this. Everyone in the class, quick. The replication fork is moving like this. It is moving like this. Of course, yes, it is moving like this. It is moving like this. Right? Right? So it is the direction of replication fork. It is also the direction of helicase. It is also moving like this, and your polymerase is also moving like this. Fine. So polymerase is moving in the direction of replication fork, Krutika. Polymerase is moving in the direction of replication fork. Fine. Now, what do you think is the possibility, Srinath? What do you think is the possibility? Do you think that DNA polymerase 3 can move in this direction? And what about the synthesis here? Don't you think that here also we need to synthesize the DNA? This is the one template strand. This is another template strand. Here also we need to synthesize the DNA. Complementary to it, we need to synthesize the DNA. And obviously here the direction of synthesis will be this, because the template strand is 5' to 3'. So here the synthesis should be in this direction. The synthesis should be in this direction. Don't you think so? Don't you think so? And focus on the details of the diagrams as well. Right? Focus on the details also. है ना? So here synthesis will be in this direction, right? This direction means like this, 5' to 3', 5' to 3', 5' to 3'. Okay. But if you will see here, I'm not synthesizing the DNA strand continuously. Can you see that? Can you see that? I'm not synthesizing the DNA strand continuously. No, not at all. Not at all. I'm not synthesizing it. This strand is continuous strand. It is synthesizing continuously. So this is the leading strand. Which strand it is? Leading strand. But here the synthesis is discontinuous. The synthesis is discontinuous, or it is the lagging strand. Which strand it is? It is the lagging strand. Now let's talk about the reason. Okay, fine, ma'am, we can see such things. We can see this is happening, right? We can see this is happening, but what is the reason behind? है ना? Our main focus is the reason. Why is it so? Why is it so? Why there is no continuous synthesis here? Right? You please focus on the detailing, people. It's like that. It is like that. Yes or no? Yes or no? So you need to focus on one thing, bache. When template strand, this is important, please pay attention. When template strand is having polarity, 3' to 5', then complementary to it, leading strand form. Complementary to it, leading strand form. Clear? This is something very important. This template strand is having polarity 3' to 5'. So complementary to it, you are getting the leading strand. You are getting the leading strand. Now here the template polarity is 5' to 3'. And here complementary to it, lagging strand is forming. Which strand will form complementary to it? Lagging strand. Which strand will form complementary to it? Lagging strand. And these fragments here, they are discovered by the scientist Okazaki. So that's why we call it as Okazaki fragments. That's why we call it as Okazaki fragment. And if you people will notice here, right? For the formation of these fragments, because this synthesis is discontinuous, right? So for the formation of these fragments, every time you need the RNA primer. Every time you need the primase, every time you need the RNA primer. Every time you need the primase, every time you need the, yes, Niharika, Leharika, Sai Krishna, everyone. Every time you need the primer. And do you think why this problem is existing here? Why such problems are there? Again, the fault of your DNA polymerase 3. The DNA polymerase 3 is having the attitude issue, right? Initially, the DNA polymerase 3 was demanding 3-OH. We were like, okay, fine, okay. You want DNA polymerase 3, you want OH, na? Okay, our primase will help you, we will give you the OH. Now the problem is, DNA polymerase is like, see, I have to move from this direction to this direction, right? I am moving from this direction to this direction. It is saying that I will move in the direction of replication fork. Listen to me very carefully. DNA polymerase 3 is saying that I am moving in the direction of replication fork. This is how I can move, okay? And I know you are expecting me to synthesize the strand in the opposite direction as well. It's like Niharika, I am moving like this, okay? I am moving like this. Okay, like this. So if I'm moving like this, right, let's say I'm coming forward. So if I have to water this side, I can do it very easily with this hand, right? With this hand, let's say here plants are there and I need to water them. I can do it very easily, very easily, very easily. But if you expect me to water the plants of this side also with the same hand and at the same time, obviously I'm going to create a mess. I'm going to create a mess. That's the point here, right? If I am moving like this, I can manage the work of one side. I can pick up the stuff from one side. I cannot do, right? And here, like let's say you are expecting कि when you are moving towards this side, when you are moving forward, okay, water the plants like this. Fine, that is doable, right? But can I do it like this? कि I am moving in this direction and I am watering the plants in this way, right? I have to water the plants in this way and this way. I say, no, there will be a problem. There will be a problem. Same is the case here. Your DNA polymerase will follow the replication fork's direction. Okay, so in that direction, when it is synthesizing the DNA, it can do it very easily. But now on the another strand, it has to make the DNA, it has to form the DNA in opposite direction and simultaneously. It's not like that, Samiksha, okay, I'll finish the one template strand and then I'll come back for another. No, that's not the case here. We have to do it simultaneously. We have to do it together, right? We have to do it together. Okay, so if I am moving in this direction like this, I have to do another work in this direction. So it's like this. Okay. For DNA polymerase 3, it's not possible. DNA polymerase 3 is like, I can try, but I cannot guarantee. Right? I can try, but I cannot guarantee. So DNA polymerase 3 is moving like this. It is coiling another part of the DNA. Right? It is trying to synthesize the new strands in opposite direction, because synthesis will always remain in 5' to 3' direction. Right? There is no change for synthesis. Synthesis will always remain in 5' to 3' direction. So somehow it will manage. Somehow it is going to manage, right? So at times it is picking up, it is holding the DNA fragment. In between it is leaving also, right? So sometimes, you know, DNA polymerase 3 is missing that contact. So that's why again and again primase is required. That's why again and again primers are formed. So that's why the synthesis here is discontinuous. So can I say that DNA replication here is semi-conservative, or can I say that it is semi-continuous, or even I can use the word semi-discontinuous as well? Yup, can I? Of course I can. Of course I can. So that is how the synthesis will be there. So when the parental strand, the template strand is having polarity this, you will get leading strand. So when the template strand is having polarity this, you will get the lagging strand. So it is MCQ, MCQ. Fine, 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 fine. So now the next thing. Okay, so once the DNA replication is done, what's next, ma'am? What's next? Don't you think that we need to remove the primers? Don't you think then we should remove the primers? Don't you think that, let's say your DNA replication is done. Okay, here you have one strand, here you have another strand. Here at this point you have one RNA primer, but because this is the lagging strand, so at places you have the RNA primer. So don't you think that now it is mandatory we should remove these RNA primers? We should remove these RNA primers. So bache, for removal of these RNA primers, we need the enzymes having exonuclease activity. We need the enzyme having exonuclease activity. Clear? Clear? Bache, when we talk about these enzymes, the DNA polymerase, I will use the short form. Right? We have 1, we have 2, and we also have DNA polymerase 3. We have DNA polymerase 1, we have DNA polymerase 2, and we have DNA polymerase 3, right? 3 is the main replicating enzyme. 3 is what? 3 is the main replicating enzyme. What is 3? 3 is the main replicating enzyme. Is that clear? Is that clear? Right? But what about the function of another? So we discussed two properties. One is the polymerase activity. Polymerase activity means whether it can polymerize the bases or not, right? Whether it can polymerize the bases or not. And second is the exonuclease activity. Exo means you know, the nuclease means something which is going to cut the nucleic acid. Nuclease means something which is going to cut the nucleic acid, and exo means the ends. Exo means the ends. So we talk about two types of exonuclease activity. One is 5' to 3', another is 3' to 5'. Means we have two types of DNA polymerase, right? DNA polymerase is having two types of activity. One can cut the nucleotides in 5' to 3' direction, like this one. This is in 5' to 3' direction, these bases. They are in 5' to 3' direction, these RNA primers. है ना? 5' to 3'. Another is 3' to 5'. Another is 3' to 5'. But this activity is used for the repair, right? It is for the proofreading. This activity of these DNA polymerase is used for the proofreading. What is the meaning of proofreading? Proofreading means now I have added the bases in 5' to 3' direction. Now I have added the bases in 5' to 3' direction. Now enzymes will move from 3' to 5' direction, and they will check that all the bases are added properly or not. If they are not added properly, that base will be removed with the help of 3' to 5' activity. What is the meaning of 3' to 5' activity? It simply means that that particular enzyme can move in 3' to 5' direction, and whatever bases are added, it can remove that. Whatever bases are incorrectly added, it can remove that. Clear? And what is the meaning of 5' to 3' activity? It is bache present in DNA polymerase 1 only, right? This is present in DNA polymerase 1 only. It is for the gap filling. It is for the removal of primer and then for the gap filling, right? This activity is used for the removal of primer, right? So the RNA primers will be used with the help of this property of the DNA polymerase 1. Okay, wait, I'll show you a table. This one, see this. DNA polymerase 1, 2 and 3. So polymerization means it can synthesize the DNA in 5' to 3' direction. So all three can synthesize that. All three can synthesize that. But why? Why 3 is the main replicating enzyme? Why it is the main replicating enzyme? Can you tell me? Why is it the main replicating enzyme? Bache, because it is more accurate. Its fidelity is more, right? In less time, in less time it will add more bases, but accurately also. So its speed is also more, its accuracy is also more. Its speed is also more, its accuracy is also more. Its speed is also more, its accuracy is also more. Clear? Clear? That's why it is DNA polymerase 3. All the three enzymes can polymerize the DNA, but they cannot, right, do it as accurately as DNA polymerase 3. So its speed is also more, accuracy. So speed and accuracy, both the things matters the most. Now who's going to qualify the NEET examination? The students that are going to answer all the questions correctly, right? They should have better speed and they should be accurate as well, right? Whosoever is going to give the NEET examination, of course bache, they all are going to attempt the paper. Sometimes their speed will be less, right? And many of them, they are not even accurate, but all of them are going to attempt the paper, right? All of them are going to attempt the paper, but who's going to qualify that? The one who's accurate also, right? Right? So that is the case. So that's why DNA polymerase 3 is having this benefit. Okay, DNA polymerase 3 is having this particular benefit that it can add the bases at a faster rate and accurately also. At a faster rate and accurately also. That's the point. Understood? That is the point. Understood? Okay. Now, exonuclease activity 3' to 5'. All the three are having this. So means all the three are playing role in the proofreading. But yeah, mainly it's DNA polymerase 2 and 1. Right? Mainly it's DNA polymerase 2 and 1. Right, bache? Right, bache? So it is helping in DNA repairing. Okay? It is helping in DNA repairing. So mainly, right, they both are helping. Now exonuclease activity 5' to 3'. It is a unique property and I think you all should focus here. Important it is. You all should focus here. It is important. The 5' to 3' exonuclease activity. What is the meaning of 5' to 3' exonuclease property? Vishal, what is the meaning of 5' to 3' exonuclease activity? That particular enzyme can move 5' to 3'. It can remove the bases from the ends. So this property, only DNA polymerase 1 is having this property, and it is very important for the primer removal. So this enzyme is used for removing the primer. This enzyme is used for removing the primer. Right, bache? Right, bache? Right, bache? So it is used for removing the primer from DNA, and then even this enzyme is going to fill up that gap. It will also do the gap filling. So this question can asked in your paper, which polymerase is responsible for gap filling and removal of, right, for the gap filling and for the removal of bases. It's your DNA polymerase 1. See, so from this side the primer will be removed, from this point also the primer will be removed. So don't you think that when RNA primer will be removed, in between the gaps will be there? Yes, when your DNA polymerase 1, because of its 5' to 3' exonuclease activity, right, because of its 5' to 3' exonuclease activity, what will it do? It will remove primer. So when it will remove primer, the gaps will be there, right? So we have to fill that gaps. It means we have to add the bases here. We have to add the deoxyribose bases here. We have to add the bases here, deoxyribose bases. So obviously this enzyme will also help in that gap filling, right? It is also having the polymerase activity, na, 5' to 3' polymerase activity. So it will use that activity and it will add the bases here. Clear, bache? It will put up the nitrogenous bases here, that deoxyribose nitrogenous bases here. Yeah, deoxyribonucleoside monophosphates here. This is what it is going to do. This is what it is going to do. Clear, bache? Clear, bache? Clear. Now the role of our dear DNA ligase. You know na, DNA ligase is also known as molecular glue. DNA ligase is also known as molecular glue. So no doubt your DNA polymerase 1 will add all the bases here, right? In the gaps, your DNA polymerase 1 is going to add the bases. But bache, the sugar phosphate, who's going to join that sugar phosphate backbone? Who's going to join that sugar phosphate backbone? Your DNA ligase. It will join that DNA strands. It will join the sugar phosphate backbone. Right? It will join the DNA strand. It will join the sugar phosphate backbone. Understood? Understood? So one more point is, there is one more point that we need to discuss. But before that, can we quickly revise it? Yes, students. Then after that, I will give you a break. For sure, I will give you a break. Hanji, tell me. Yes? Okay? Done? So, the next story. I told you that, see, in the nucleoplasm, DATP, DCTP, DGTP and DTTP. Okay, DTTP, they are present. DCTP, DGTP, DTTP, DTT, all of them are present, right? I told you now, they are present. But they are serving a dual purpose. This is important, given in NCERT. Please listen to me. They are serving a dual purpose. Okay, they are serving a dual purpose. Okay, DATP, DGTP, DCTP, DTTP. This is deoxyribose adenosine triphosphate. If anyone is having doubt, that's why I'm writing it. But if you have doubt, this is deoxyadenosine triphosphate. Right? This is deoxyadenosine triphosphate. Actually, these are deoxyribose nucleoside. The word should be nucleoside triphosphates. They all are what? They all are deoxyribose nucleoside triphosphates. Now, obviously, I told you that right here. Just come to this side. So, here you know that. Can you see that, bache? DNA polymerase 3, this is the helicase. Helicase is moving in this direction. DNA polymerase 3 is moving in this direction. So if it is moving in the direction of replication fork, then it will synthesize the leading strand. It will synthesize the leading strand. But if it has to move away from the direction of replication fork, then it will form the lagging strand. I told you it is going to form the lagging strand. And even I told you about the template as well. Hai na? Template as well. You can see this diagram also. Single stranded binding protein, the helicase and the topoisomerase, that is removing the tension. So see this diagram also. So see, this is the leading strand. Here the template is having polarity 3' to 5'. Here template is having polarity 5' to 3'. So lagging strand is there, right? Lagging strand is there. Can you see that? Right? So they are the most recently synthesized strand. So means this strand will synthesize first. This strand will synthesize as first. This one as second. Okay. Okay. Understood? Sure? And that's the diagram from NCERT. So continuous and sorry. So number one, it will be synthesized first, second, third. Right? So it will be synthesized first, the older one. Then this, then this, then this, then this, like this. Okay, so in the Telegram group I will share the animated video also, right? I'm going to share the animated video also, and you can use that animated video, right bache? You can use that animated video, then there will be the better clarity. Now I was coming to a point, right? I was coming to a point that basically we are adding the bases here, right? If we are using DNA polymerase, we are adding the bases here. Now I said that we have this, and they are serving dual purpose. Then what is the meaning of my line? See, we know that in the DNA strand, let's say here A, T, C, G, randomly I'm giving you one example, so please listen to me carefully. right? I'm giving you one example. So complementary to A, T, complementary to T, A, G, C, G, C, G, C. So they are, you know that they are the monophosphates here. Am I right? They are the monophosphates here. So bache, when we will pick up this DATP, let's say here I have to add the adenosine, I have to add the adenosine monophosphate. So I will pick up this DATP, right? When my DNA polymerase 3 will try to put it here, when it will try to put it here, so this DATP, you know that up to monophosphate it's fine. When we add to other phosphates, then they are very high energy bonds, right? Then they are very high energy bond. This is in NCERT. This is in NCERT. MBBS in my dream. Start reading NCERT properly. Otherwise, MBBS will just be your dream only, right? The dream that will never become reality. Okay, so I have to, when my polymerase is going to add the bases here, so it will pick up what? DATP. So when it will pick up DATP, other two phosphates are high energy bond. Other two phosphates are high energy bonds. So in that time, so at that time, what is going to happen? These two phosphates, they will release their energy. These two phosphate bonds, they will break. They will release their energy. That energy will be used for the polymerization, right? That energy will be used for the polymerization. That's why we say that they are also acting like a substrate and also providing energy for polymerization, right? So all these nucleoside triphosphates, they are also acting like a substrate. This is their dual purpose, right? This is their dual purpose, right, bache? This is their dual purpose. Okay, so it is the substrate as well that we are going to use for synthesizing our DNA, and it is also for providing, right? Also providing, it is also providing energy. Is that clear? It is also providing energy. MBBS in my dream, it's not like that. It is just a warning for you. Okay, don't take it on your heart. It is just a warning for you that bache, start reading the NCERT properly. Fine. We just have 3 or 4 more months. So start reading the NCERT properly. Okay? Okay, so this is all about the DNA replication. So I'll ask few questions and see, I have added the differences for you as well. Fine. So see, here the main enzyme is DNA polymerase 3. Here it is delta and alpha. Okay. Here DNA topoisomerase 2 is there. That is DNA gyrase. Here simple DNA isomerase is there. And here, while joining the Okazaki fragment in prokaryotic cell, the DNA ligase will use NAD. But here in eukaryotic cell, it will require ATP. Right? It will require ATP. Right? So here one more table is there for you in which the function of all the enzymes is written. So please take the screenshot. Right? Please take the screenshot. Guys, please take the screenshot. Okay? Okay. So now let's read it from NCERT. This is the summary of the DNA replication. You can see the replication bubble and 2 replication forks there, bache. So see, this is the direction of your replication fork, and in same direction helicase is moving, DNA polymerase is moving, leading strand. So if it has to move in opposite direction, right, then it will be the lagging strand. So this is the strand which is synthesized first, then second, then third, like this. Okay, so it is ultimately your DNA polymerase 1 that is going to remove primer, and it will play a role in the gap filling. Its polymerase activity will play a role in the gap filling. Please do not miss these points. Okay, okay, so fine, I didn't add it. Okay, so bache, I don't have the NCERT screenshots for the replication. right? I literally don't have the NCERT screenshots for their application. So all I can say is that after the class, please read it from NCERT. That line is there, na, nucleoside triphosphate, they serve the dual purpose. They are acting as a substrate and they are providing the energy. It simply means when we will use them, the two phosphate bonds, they will be released, they will break, they will release their energy. That energy will be used for the polymerization. So they are substrate also, they are providing energy also. The points about the polymerase 1 and 2 and 3, they are important, right? So can we quickly revise it? Yes, bache, very good sign. Can we quickly revise it? Can we quickly revise it? So the leading strand will form complementary to, the leading strand will form complementary to, yes students, the leading strand will form complementary to, Anjani, don't you know the syllabus, bache? The leading strand will form complementary to 3' to 5'. Excellent. Excellent, Sadaf bache. 3' to 5'. The leading strand will form complementary to 3' to 5' template strand. Excellent, Samiksha. Right? Lagging strand will form complementary to the strand having polarity 5' to 3'. Which enzyme is going to remove the primers there? Which enzyme is going to remove the primers there? Which enzyme is going to remove the primers? DNA polymerase 1, and that gaps will be filled by, and that gaps will be filled by, and that gaps will be filled by DNA ligase. Excellent. Bhai, I just told you that gaps will be filled by DNA polymerase 1. DNA polymerase 1 with its polymerizing activity will add the bases there, the complementary bases there. And finally, DNA ligase will join sugar phosphate backbone. You at least listen to my question. Gap filling, this is the exact word that is filled by DNA polymerase 1. And who's going to ligate that? Who's going to ligate that part with the other DNA part? Obviously, your DNA ligase, which will join the sugar phosphate backbone, right? It is the one which is going to join the sugar phosphate backbone. Understood? Understood? Okay. My next question is, how many replicants are there in the eukaryotic DNA? How many replicants are there in the eukaryotic DNA? How many replicants are there in the eukaryotic DNA? How many replicants are there in eukaryotic DNA? Guys, I really don't think that you have attended the class. I think you people were sleeping. Excellent, Samiksha. Polyreplicants. Eukaryotic DNA is polyreplicant. It is having many sites from where application can start. What is a replicant? The site from where the application can start. Right? The site from where the application can start. So in the eukaryotes, there are many replicants, many sites from where the application can start. But in the prokaryotes, there is only one site, that is your ORIC. Okay, ORIC. So is helicase is going to open up the DNA strand in one go, or it will do it slowly, slowly? Yes, or is it going to open it up slowly, slowly? Slowly, slowly. Very good. Slowly, slowly. Okay. So who gave the, yes, who gave the experimental proof for the semi-conservative nature of DNA in eukaryotic cell? Who gave the experimental evidence for the semi-conservative nature of DNA replication in eukaryotes? This is my next question. Quick. Quick, quick, quick. Everyone answer my question. Obviously, you are giving the incorrect answer. You are giving the incorrect answer. Right? You are literally giving me the incorrect answer. But I specifically mentioned in eukaryotes who gave the experimental evidence. The answer should be Taylor and colleagues. Why? Because they experimented on Visia feba. That's a plant. That's a plant. And plant is a eukaryotic cell. Plant is a eukaryotic cell. Right? It's a eukaryotic cell. So you are giving the incorrect answer. It is a question in a previous year paper. Literally, it is a question in a previous year paper. right? They mentioned it. Who gave the experimental evidences of semi-conservative model of DNA replication in eukaryotes? If the word is eukaryotes, then you are talking about the Taylor and colleagues. They experimented on fava beans. They used the radioactive thymidine. Fine, they used the radioactive thymidine. Fine. So wake up. Okay, wake up. So guys, I am not going to continue the chapter further. Okay, this is what I am going to teach you today. I will take another part of this session because all the topics are important, including transcription, different types of RNAs, translation, genetic code, DNA fingerprinting, and human genome project. How can I forget? These are the next 6 topics, and you need another 6 to 7 hours for them, right? And I really don't want to rush it because I have seen your responses today. Okay, so I'm not feeling like that I should proceed with the class because I don't think that you'll be able to grasp it today. Okay, so let's take it in 2 parts. We'll let you know when I'm going to take the second part. If possible, I'll take it tomorrow or day after tomorrow. Okay, chaliye, thank you so much. So we'll wait for your comments, and I hope you people enjoy this part. You people revise this part, and please be regular and consistent for the second part also. Okay, and yes, tomorrow at 11 AM I'm going to take the special class. Okay, I will take the special class where we will be practicing your questions till this replication part. Okay, so I am not going to miss special class. Be the part of that class, and do watch this video, guys. The forms to be filled other than NEET, right? That is important for you, right? That is actually important for you. Okay, so take care. Thank you so much, people. Good.